19h. Ok, d'accord.
Okay, so
On attend,
thank you
ouais.
everyone for joining us for this afternoon. And the first speaker is Stéphane Mallat, who is going to talk about multi-skill conditional learning and sampling with application in physics and English.
Well, thanks very much for the invitation to you and Tony and Marilou. So this is going to be a work in conjunction with many people, among which Valentin, who is here, Florentin also, who is here, and Giulio, who was here, and many other people I'll be speaking about during the talk. So I'm going to shed a slightly different light to the problem of sampling than the one that was given, which was more from the sampling perspective, by trying to understand how we can simplify this problem by taking advantage of the structure of the problem. So applications will be learning physics or probability distribution in general, and exactly as Marilou was describing, I'll be trying to learn the energy or the log probability of distribution. So this is a Gibbs energy. And the first type of application will be for physics. The simplest kind of problem is 5-4 that Marilou spoke about, but I'll be speaking about. And then we'll move to more complex physical processes, including turbulence. But I'd like to show that the same kind of mathematical framework will also apply to much more complex images, such as faces. So there are really three problems we are all turning around. The first type of problem is to understand how to do a parametrizations of this probability distribution, namely of these energies from prior that we have, and do so that we can, one, guarantee a fast optimization of the parameters, and two, be able to sample these processes with relatively fast algorithms. And what I'd like to try to show is, for the kind of problems I'm showing here, one key element to answer to these problems is to understand how scales interact and to model and then understand these scale interactions that we'll see can be local. And the fact that they are local means that you can circumvent the curse of dimensionality by reducing considerably the number of parameters involved in this distribution. So let me very briefly begin by the two problems that you all know well. The first one is the estimation of the parameters. So you can do that with maximum likelihood approach and do gradient descent on the maximum likelihood. And of course, the convergence of this gradient descent is going to be controlled by the Hessian. And if you are lucky enough that you have a convex problem so that the minimum eigenvalue is positive, the whole issue is to control the condition number of this Hessian. So that's for the parameter estimation. Then there is the sampling problem. Suppose that you've already identified your parameters. You want to sample your distribution. Again, that has been discussed at length. The simplest approach would be to do Langevin dynamics, which basically amounts to try to minimize the energy term. This is the grad x log probability, plus the random fluctuation, which is provided here by the white noise. And we know that such algorithms converge, but it can be incredibly slow. And again, that was very well shown by Marilou this morning. In particular, when you have a double well problem, the whole difficulty is to go above the barrier, to go from one to the other. And you have this kind of trade-off explorations that was also described by the talk of Alain Durmus this morning. So the question that I'm going to ask is it possible to avoid all these technical problems by essentially transforming the problem into a convex problem by using the problem structure? And what I would like to try to show is that it's possible, it seems to be possible, for a range of problems which is surprisingly large. So exactly as in the previous case, the rate of convergence, if you are in the case where the Hessian is positive, is given by the Hessian, but here the Hessian computed as the second derivative relatively to the variable x. So in these problems, we have two Hessians that we want to control in order to be able to identify the parameters and in order to sample the field. Okay, so the idea is to try to look in this probability distribution for strong sources of regularity so that you can reduce the dimensionality of the problem. And one of the key observations in physics was provided by the renormalization group theory initiated by Kadanoff and then Wilson in the 1970s. And the key idea is to look at a random field. This is a cosmic web in cosmology at different scale. So to do so in the Kadanoff picture, you average subsample, and so on. So you obtain a field at different resolution by doing so. And then the idea is to look at the probability distribution of each of these fields at this distribution. Now, if you are away from phase transition, you can hope that by averaging, you are going to converge to something which is going to be potentially Gaussian. But what you would like in general is to understand this evolution. And one way to do it is to parameterize this probability distribution. In physics, these would be called the coupling parameters, and look at the evolution of the coupling parameters across scale. And the amazing result obtained by Wilson is that essentially, if you look at it as a dynamic system, at a phase transition, you have a fixed point if you have renormalized the parameters. In other words, these parameters are not going to depend anymore on J, which means that it's incredibly regular across scales. Okay, so what we would like is to understand the regularity of the evolution, but we are rather going to move from coarse to fine because we are going to do synthesis. So we want to understand how we move from a coarse scale to a fine scale. Moving from a coarse scale to a fine scale, that means getting the conditional probability distribution of the fine scale given the coarse scale. Now, this probability distribution, if you know it, then you have a kind of Markov chain. You can compute the probability distribution of x as the probability distribution of the coarse scale, and then the transitions across scales. Now, the whole question will be to try to specify these conditional probability distribution. Now, the information in xj minus 1, you have xj, but you should be able to reconstruct xj minus 1 with some other missing variable. What are the missing variables? These are what you would say the the degrees of freedoms corresponding to the high frequencies. And if you are able to indeed decompose xj minus 1 into a coarse field and the orthogonal complement, then you can write the conditional probability as just being the probability of the missing variable xj bar given xj. Okay? And the question then is to find a coordinate system to represent these orthogonal variables.
Why is the chain Markov?
Oh, it's just because the information here is included into here. So there's nothing deep here. Okay, so you want to decompose xj minus 1 into xj and xj bar. Now, in these problems, we know that the probability distribution often have a kind of equivalence to translation whenever you have some stationarity, rotation, potentially dilation. So it makes sense to use these groups to define the coordinate system. And what we're going to do is to use a wavelet basis. So what is a wavelet basis? A wavelet basis is obtained from a single wavelet, psi over there, that you are going to dilate by factor 2 to the j, translate on a uniform grid whose interval is 2 to the j, and rotate. So these are typical wavelets rotated. And if you adjust the construction of your wavelets, you can get an orthogonal basis. What does it mean? It means that if you begin from a field like that, xj minus 1, you can decompose it into a coarser field, and the orthogonal complement is given by the inner product with wavelet, which essentially gives you the local variation of the field within the different direction, horizontal, vertical, or diagonal. Now, when you look at the wavelet coefficient here, they look a bit like a white noise, okay? And then we're going to continue this transformation. Xj, you sub-decompose, and so on. So this noise is not Gaussian, typically, but the power spectrum seems to be white. And that's something that is going to be really important. Same thing done on a phase. On a phase, this is the coarse phase, even coarser phase. And these are the wavelet coefficients, which essentially extract the contours at different orientations. Okay? And I'll come back to that. It's absolutely not Gaussian, but the spectrum of the underlying process, if it's stationary, remains one. Okay, so what are we going to do? We are going to take the probability distribution. I don't know if there is a pointer. No, because I can't point on my screen, it doesn't show. Super, merci. So, it points. Oui, excuse-moi. Okay, so the probability distribution P of x is defined at the coarse scale probability distribution and then all the transition. So the object that we're going to model are these conditional probabilities. We don't try to model directly P of x, but each of the conditional probability of the high frequency given the low frequency. And we're going to build an energy model of these conditional probability. A very important element is that each time, exactly as in the renormalization group, we renormalize the amplitude of the wavelet coefficient so that they have a variance of the order of 1. That will, if we were able to build such model, allow to do a coarse to fine sampling. We begin at the very coarse scale. If we have a model, we just sample the model, and then we go to the next scale. To do that, we synthesize the high frequency wavelet coefficient knowing the low frequency. Once we have this, we apply the reconstruction, it gives us the next scale. Then we sample the next set of wavelet coefficient, we get the next scale. We sample the next scale, and so on. So the idea is that's the only object that we need to model. And the claim that we're going to try to show is that these probability distributions are much simpler to model. In what sense? In the sense that very often they are local. In other words, they define a Markov conditional field, whereas the original field has long-range interaction. These will only have short-range interaction. Thanks to the renormalization, we get the Hessians which are well-conditioned so that we have a fast convergence. And often, we've observed, these log probabilities can even be convex so that you have a well-conditioned and fast Langevin sampling algorithm. So these are the three elements that I'm going to try to show on different examples. Now, first let me begin with the Gaussian case. In the Gaussian case, you have a covariance matrix. This is the probability distribution. And so the parameters of your model is given by the second order moments, and here the inverse of the Gaussian matrix. Now, if you have a covariance which is badly conditioned, if kappa is the condition number, you easily verify that the identification of the covariance coefficient and the sampling are going to have Hessians whose condition number essentially depends on the condition number of k. So if the covariance is badly conditioned, all the problems are going to be badly conditioned. Now, why is that an important case? Because if you take a typical image, whether it's going to be a phase or a turbulent flow, if you consider it as a stationary process, that means that the covariance is going to be diagonalized in the Fourier basis, and you can look at the decay of the power spectrum, the eigenvalue of the covariance. And you are typically going to have, in turbulence, a power law decay. What does that mean? That means that the ratio between the smallest and the largest eigenvalue is going to be very large. The condition number is going to depend upon the system size to the exponent eta. Now, of course, that's not the only problem, because if you try to model this field with a Gaussian field, you get something which is a very bad model. So we are facing this ill conditioning problem, but of course we also face the model error. Why wavelets are going to help? Because the wavelet transform essentially do a sub-decomposition which is local in Fourier. If you take an image like this, if you sub-decompose it on one level, basically you get the low frequency, and the high frequencies are covered by the wavelet coefficients, which here extract the edges. At the next scale, the low frequency is sub-decomposed into an even lower frequency, and the other frequency bands, and so on. So, if we come back to our problem of a Gaussian process, the difficulty comes from the fact that the eigenvalue explodes, so the ratio between the largest and smallest eigenvalue is huge. If you decompose in a wavelet basis, it essentially corresponds to decomposing the modulus into dyadic intervals. Now, over such an interval, the eigenvalue varies by a constant factor, which is the same here, then over this interval, then over this one, then over this one. So if you renormalize by a coefficient which depends upon this amplitude, all the eigenvalues are going to be of the order of 1. And that's what this theorem tells you, is that if you take a singular operator which has these eigenvalues that grows like omega to the power minus eta, after renormalizing, all your Haitians have a condition number which remains of the order of 1, whatever the scale. What that means is that you're going to have a fast learning of the parameters and a fast Langevin sampling, but here it's trivial because it's a Gaussian process. Okay, so let's move now away from the Gaussian process and consider the case that Marie-Lou spoke about, which is 5-4. So 5-4 is a probability distribution which has a Gaussian term, which is the kinetic energy, which is here given by the Laplacian, plus a nonlinear potential, and the nonlinear potential has a double well. So it's a non-convex probability distribution, and that's when the temperature is above the critical temperature. This is the inverse temperature, so you get a field as a realization where most values are close to 1 or minus 1 and somewhat disordered. But when you reach the critical temperature, you see appearing long-range correlations, which appear here, and this is the phase transition step. Now, if you look at this probability, but at different scale, what do you observe? If you are above the critical temperature, at very coarse scale, it gets Gaussian. At fine scale, you have this. But if you are at the critical temperature, or the potential remains identical, that's this idea that the coupling parameters don't depend upon scale when you are at the critical temperature. So you have a non-convex problem. But if now you look at the probability distribution of the high frequencies given the low frequency, they are essentially convex, and when I say essentially, because that remains to be proven, you need to choose well the wavelets for that, and well conditioned. So why is that so? Because essentially at coarse scale, if you have a sample, you already more or less know you are moving like this. You never have to go from here to here. You go from here to here at the coarse scale, which puts you here or puts you here, and then you go like here. So you don't go across the barrier, and this is what allows you to sample without facing the non-convexity problem. And I'm going to show that's the rate of convergence of an MCMC Metropolis Hastings simulation. That's the number of iterations you need before your chain decorrelates. That's when you're reaching the critical temperature, it gets much slower. That's the speed of decorrelation compared to when you are away from critical temperature. This is 2,000 iteration over the whole system size. And this is if you do the same thing, but on the conditional probability. Two properties. First of all, it converges much faster. That's 30 versus 2000. Second, all these curves are the same at all temperatures because the conditional probabilities don't suffer after renormalization from these instabilities. Okay, now that's the first part. what that shows is that if you have a problem which is intrinsically multi-scale, you'd better sample the variation from one scale to the next. The next problem, of course, is you want to go beyond 5.4 and deal with much more complex images, such as cosmological images. This is matter density, this is turbulence, and faces or natural images. Okay, so in this framework, what you need to model are the conditional probabilities. Now, xj is the low frequencies that you can sub-decompose into wavelet coefficients at coarser scale. So what you need is to compute these conditional probability of fine scale coefficient given the coarser scale coefficients. Let's try to build a simple linear model. So instead of moving immediately to DeepNet, we're going to try to see how far we can go with simple linear model. A linear model means that the energy of these conditional probabilities are going to be a linear function of a set of nonlinear function of the field phi. To build such a linear model is in fact equivalent to compute the probability distribution with a moment matching algorithm. You can show that Pj is the distribution which are going to have the same moment as P relatively to phi and a maximum entropy. So what kind of moment? The first idea that comes to mind is to say, okay, we're going to specify the second order moments. Second order moments are going to define Gaussian processes, but that's not just that. If you look at the correlation of the wavelet coefficient across scale, they live at different frequencies. So they are non-correlated. So second order moment gives you no information about interactions between scale or interactions between frequencies. In order to capture that, you need to introduce nonlinearities. Now, what kind of nonlinearities? The reason why these correlations are zero is because of the phase oscillation. The phase oscillate at different rates, and that's because of that the correlation is going to cancel. So if you want to avoid this cancellation, you want to eliminate the phase, or at least separate the phase and the modulus. So that's what we do by putting a nonlinearity. We could put here a ReLU, but mathematically here it's going to be simpler to put a complex modulus because we have complex wavelets. So we are going to look at the correlation of the field and the other field at different scale after the modulus. And the modulus is essentially bringing the Fourier support to zero, so that these two Fourier support are going to overlap, and the correlation between the two modulus. Now, I'm going to go briefly on that, but if you want to reduce the number of moments, you have big covariance matrices. You want to compress these covariance matrices, and you can show that, again, the way to do it is to retransform them into a new wavelet basis. And so you have a cascade of wavelet basis, nonlinearity, wavelet basis. That's what I'm going to illustrate here. This is your image. This is the first scale of wavelet basis, like that. You apply your nonlinearity, the modulus, and you let the value, and you reapply a wavelet transform. And then you renormalize all the coefficients at each of the layers of your tree, and then you compute the covariance. So that looks like a bit like a deep net, but we don't learn anything. All the weights are in fact the decomposition in your orthogonal basis, and you get these covariance value. Okay, if you now build your model by identifying the theta with the maximum likelihood procedures, there are several things. First of all, in these cases, you have few parameters, so you can identify your model from a single realization. So from one realization, we identify the theta, and then we sample the random process, and these are the samples of the random processes. So you can see that in these cases, which are essentially stationary ergodic fields, physical processes, capturing the scale interaction with a linear model is enough in order to reproduce fields which have the same visual properties, and we checked up to the order 4 moments and the structure function, and they have the same statistics essentially. So you can build models with this approach across scales, which are quite precise, well beyond the toy models. Let me now finish by moving to faces, or structured images, which are typically non-ergodic. Here I'm going to use the score diffusion approach, which has been described before. So let me just remind you. The idea is you take an image and you run an Ornstein-Uhlenbeck process, which essentially adds white noise until the white noise dominates. You essentially converge to a Gaussian white noise. So you have a stochastic differential equation. This equation, you can invert it. And to invert it, what you need is to compute the score of your probability distribution. So the whole problem is to compute the score of this probability distribution. And this is what is going to be done with a deep network in the standard approach. So this is now the work. I forgot to mention, all the previous work that I mentioned was the work done with all on these conditional Markov conditional wavelet model are done by Thierry Marchand, Misaki Ozawa, and Giulio, who is here. So the problem here of this diffusion model is that you need a very large number of steps to go here. And you can think of it, you begin from a random process whose power spectrum has a 1 over omega decay, and you get to something which is white. So it takes a long, long time, in particular, to whiten all the low frequencies, which have much more energy. So that's the work of Florentin, who is here, and Vincent de Bortoli and Simon Coste. And the idea here is to say, okay, let's apply the same strategy. You take your image and you decompose it into a coarser image and the high frequencies. What we're going to model is the high frequencies given the low frequency. And to do that, we are going to build the same diffusion and compute the score of the high frequency wavelets given the low frequency. So we compute the score of this conditioned to that on the way that we introduce noise. Then we're going to do the same thing at the next scale, that we're going to be noise to compute the score, and finally at the coarse scale. Now we're going to then synthesize. So the idea is essentially the same coarse to fine. We first synthesize the low frequencies, then we synthesize the high frequency wavelet coefficient, then at the next scale, the high frequency wavelet coefficient. Why doing that? Because you see the time, the number of time steps that you need at each scale doesn't depend upon the scale, because essentially you have something which is self-similar. The process, if you dilate a face, it looks like a face, okay? And the noise is quite self-similar. So the timing, the reason why you need a time which essentially has to accelerate when you sample this score diffusion is because you have many scales. When you separate the scale, you can accelerate these score diffusion. Now, so that's the thing. That's the computations that were done by Florentin in particular. So these are images synthesized with a scheme where you don't separate the scale with very few steps. These are images synthesized by using the same number of time steps, 10 time steps. And you can see that the quality is much better because it converges. The convergence is faster. And these are the convergence curve as a function of a measure of quality. Now, the last important thing is that even when you have very structured images that doesn't look quite like 5-4, you have a local dependency. In other words, you can build a model of these images by each time computing the conditional probabilities of the high frequencies given the low frequencies. But to build a model of this high frequency, you only need to know the conditional probability restricted to a very small neighborhood. This is a 13 by 13 pixel neighborhood. So the conditional probabilities here are essentially going to be Markov field. And the log probabilities because you know that it's a local field, you can model it again with a network, but a neural network whose receptive field, in other words, all the calculations are going to remain completely local. And that speeds up a lot the calculation, and it makes the property of the model simpler to analyze. And that's the work that was done by Florentin, Zara, Kadiskos-Kodai, and Eros Simoncelli. So these are examples. Here is the original image. Here's a coarse image that was defined by a 40 by 40 image, so it's very blocky. And what we are going to do from here is to synthesize the high-frequency images from the score that was learned on a database. So it's the same kind of algorithm than the score diffusion algorithm. The only difference with the previous example is that all the conditional probabilities are computed locally on 13 by 13 neighborhood. And you can see that as the scale increases, here are the fine scale model. You can see that you recover very fine detail given that you only moved from here and a probability distribution model. These are the original images, and all this is completely local. The only non-local element is essentially at the very coarse scale, but these are in reality very small images of 40 by 40 pixels. So, to finish, I think that we need to interact a little bit more in between the two communities on one side, sampling in the mathematical side, and the other side, let's say, harmonic analysis and understanding of the structure. And that was a little bit the sense of this work that we initiated with Giulio. What is interesting is that here physics is really giving some very powerful intuition on how to attack the problem. And in particular, the renormalization group, it's interesting to read the first paper of Wilson because he discovered wavelet bases, and his first paper was written within wavelet bases. Then people moved over Fourier to analyze the renormalization group. The only thing is that the day you understand well the structure of these wavelet bases, you can build these factorization. And these are the two ideas. Essentially, these conditional probabilities can be local, so essentially Markov, and that kills the curse of dimensionality. And they can be well conditioned after the scale interaction. So one question beyond this problem of generation, of course, is whether that kind of ideas can extend to understand a bit more the deep neural network architecture, but that's beyond. So let me just go back to my co-authors again. The first part on all the renormalization group work was done with Thierry Marchand, Misaki Ozawa, and Giulio. The work on score-based generation modeling was done by Florentin, who is here, and Valentin de Bortoli and Simon Coste. And the last part, which shows that you can still have local models, even with very complex images, was again done here with the team at Flatiron and Florentin. And that's it. Thanks.
Do we have questions?
Thank you. So, thank you for this very nice talk. So, it's interesting because in sampling for computational physics, we have also this idea of conditioning to kill metastability. One question we have always in this context is that we don't know with respect to what we should condition. I mean, it's about this finding the collective variable, this reaction coordinate. It seems that in this context, there are some kind of universal reaction coordinates, which would be some universal way to coarse grain the problem, whatever it is, in some sense. And so my question is, do you think it's related to the fact that you look at images, or to these problems where the renormalization group applies, or is there a hope to indeed build some kind of universal reaction coordinates in some sense? So,
yeah, I have a tendency to think that it's something which is somewhat universal in the same way that the Fourier transform is universal, because you have local interactions, and the local interactions are going to propagate in space, in a space. And you are doing the coarse graining on that space over which the local interaction propagates. So this is why it's a natural thing. This is why in physics all over, coarse graining appears. Even in molecular dynamics, you do coarse graining. You do it in geosciences and a bit everywhere. So yes, and that's not my idea. This is a very standard idea. And wavelets are here just to find the orthogonal basis. But it's this classic idea that you want to do that. Now, there is something interesting is that sometimes coarse graining doesn't eliminate the double well problem. And that's what's happening, for example, when you're at the phase transition. You still have, at the very coarse scale, or if you take a face, you coarse grain the face, you still have a complicated object. But you have a complicated object in a much smaller dimension. Instead of working on a 1000 by 1000, you work on a 16 by 16 or 40 by 40 image. So at one point you may have a hard problem, but it's on a very small dimensional problem. And then you condition. What is interesting in phases is that the model, in fact, of the high frequencies is stationary and is local, but it's also stationary. So all the non-stationarity has been put into the coarse field.
So for example, in your minus log of P,
Yeah.
idea, the P depends on the image or is done once for all? You see when you reconstruct, so it's
Oh, you mean
so here or maybe before when you were starting from a face and reconstructing it by just the backward SDE, the backward yeah, exactly this one.
Yeah.
So here the log of P.
The log of P is learned once forever.
But for one image or for over?
No, for a database. This is a probability distribution which is learned, but then it's conditioned when you synthesize, you condition it. But you learn it's a conditional probability distribution, yes.
So in this problem or in the physics one, do you have a way to quantify how good you were in generating the field?
Yes, in the physics one, what we did is the classical tools in physics to evaluate the quality are bispectrum, trispectrum, so second, third, fourth order moment or structure function. And we showed that we are matching all these moments. That was done in, that's a paper that we're finishing. And in the images like faces and so on, it's just visual quality, but there is people have come out with numerical index of qualities. And we are not as good as the huge neural networks and so on. But what appears, what we've been showing in the case of faces is that it's local in the sense that when we change the size of the neighborhood, the quality of the model doesn't change. It's really the dependency seems to be very local.
I have a question closely related to what Tony just asked. So basically, I'm wondering whether this universal basis can be applied to biophysics models. So there actually people, it's quite important. They also consider some orthogonal basis, but it's quite important that for this basis has to be chosen depending on the application. For example, different systems, you have different invariant distribution, and this they have to consider different spaces and choose bases. I'm wondering, do you have in this community, for example, images or problem like this, do they consider different spaces?
Okay.
So sorry. So basically, the dominant basis functions has to characterize the non-local effect you just.
So I have to characterize. Sorry, the metastabilities. Okay, so the idea here is that the basis doesn't depend upon the metastability. The basis depends upon the space. So if you take, for example, in chemistry, molecules, there's two ways to do it. Either you say, oh, they all live in the 3D space and I build a basis in the 3D space, or you say they live on a graph and then you have to build a basis on the graph, and people have been building a multi-scale basis on the graph. But the idea is that you don't adapt the basis to the probability distribution. You adapt this basis to the space which embeds. The reason why these problems have a level of simplicity is because we have the topology of the space, the 3D space, and that's what allows to do analysis. So I don't know if I answered well.
Yeah, for example, you consider differential operators.
Yes.
And I don't know, so it seems that for Laplacian, I will choose one basis for the space. If I compute, for another differential operator, I will have to, for numerical purpose, change and consider another. That's what my question.
Okay, so that's a very well phrased then. The answer for that is no, you choose the same wavelet basis for all pseudo-differential operators. So pseudo-differential operators, none of them is going to be diagonal, like in a Fourier basis. If you try to diagonalize your operator, you have to change the basis for each operator. But for all these operators, they are going to be represented by a band matrix, local interaction. So you don't have to change your basis because it's stable for essentially all differential and pseudo-differential operators. But they don't diagonalize any of them.
Once you have this nice generative model, so it has a simpler structure than if you just use any network. So you might try to interpret this transition probability across scale. So for instance, in the case of turbulence, has anybody tried to interpret it?
Yeah, that's the goal also, but to do that you need dynamics, because turbulence as a pure slice, it's much easier to understand really the dynamics of these coefficients. That's where the PDE are. It's on the dynamics. And that's why we're telling you we need to move to dynamics and now try to understand how these models evolve across time to understand whether why they are lower dimensional and so on.
Okay, so well, let's thank Stéphane.
Thanks.
Now we're ready for the second talk of this afternoon, and it's Arnaud Doucet from Oxford. Is going to talk about denoising diffusion model, Schrödinger bridge, and generative model and inference as well.
Thank you for the invitation. So thanks for the organizers for inviting me to Paris. I haven't come to Paris for 4 years, so it's always good being back. So I'm going to mostly talk in this talk about the work I did at Oxford University with actually Valentin in particular, again, and other PhD students in Oxford. And also, if I have time, I will also basically discuss some recent work I've been doing at Google DeepMind, which is essentially on the use of this kind of score-based idea to do some kind of standard Monte Carlo sampling. Okay, but I don't know if I'll have time. I'll have a slide at least to discuss it. So basically, what I'm going to talk about in this talk is about something that has been mentioned by Stéphane Mallat in his previous talk. It's about this novel class of generative model, which are known as denoising diffusion model. Okay. So first, I will have a very pedestrian introduction of denoising diffusion model. So if there's one thing to kind of basically remember by now, this talk is how those techniques work, and we see that actually they are actually really interesting and very, very powerful. Okay. So generative modeling. So I know you're all aware of basically of it. I mean, even if you're not working in machine learning. So typically, obviously, you've seen, for example, image synthetic images in the literature, this kind of deep fake that have been around for actually quite a few years, actually. So this is something of major area in machine learning. I would say that at DeepMind, actually, I don't know, but a good quarter of my colleagues must be working on generative modeling, okay? So it was basically starting, maybe, actually, there was a lot of work before, but I think I would say in machine learning, really, that was driven by a VAE, like variational encoder, 2014, and there was this kind of really landmark contribution by a good fellow and his colleagues about generative adversarial network, and it's been growing over the past few years, actually. Okay, so why are people interested in generative modeling? Okay, so maybe good to understand why people really care so much about this problem. Is not because they are interested in essentially, simulating, synthesizing a fake image per se. Is basically because somehow what they want to do is that they want to use, they have access to the kind of big, like a kind of a database of, say, images that are on internet, database of, say, protein that are also accessible, and they want essentially to use this kind of information to build some kind of data-driven prior to, so as to either simulate new proteins, say, simulate new videos with given characteristics, and so on and so forth. Okay. So similarly for text, basically, typically the idea is to kind of build all this information, build up some kind of data prior model based on this information, and later on you're using this kind of information so as to basically in the context of either conditional simulation or or basically this kind of interesting kind of problem. Okay. So I'm not going to elaborate a bit more, but it's really the kind of key problem in machine learning. So the state of the art about basically in terms of generative modeling, I think I would say it was until 2020 generative adversarial network, which is perhaps the most cited paper in CS over the past 10 years. Okay, and then suddenly, essentially, there was a group in Berkeley and a group in Stanford, basically a group with Jonathan O and the one with Yan Song in Stanford, who basically kind of essentially they read this paper by Soldichstein in 2015. They kind of revisited it, and they realized that basically they could come up with actually amazing results so as to perform essentially generative modeling. And ever since, it's basically dominating this literature. If you're following a little bit the kind of AI literature or AI news, you might be aware of some kind of system that have appeared recently, like DALI-2, ImageGen, or Stable Diffusion, which are this text-to-image essentially system where you you have some kind of caption. You say, I want to basically see 3 bears dancing on the moon, and it's going to generate you synthetic images of basically following this caption. So it's kind of really, it has really become extremely kind of huge over the past year, essentially. And all the systems are based on the class of denoising diffusion model. So it's very difficult to follow the literature because there are about 2 or 3 papers every day on arXiv, new paper on the subject. But thankfully, Valentin and my PhD student James Thornton have a kind of website where you can basically follow what's going on. Okay. So why those techniques, why did they become extremely popular? Well, simply because they do better than GANs, actually. So there was this paper by OpenAI. So it's in like March or April 2021, which in this area is like a very long time ago. And they have this paper where they really did show that on various metrics, diffusion models were doing much better than GANs on image synthesis, and they are also much easier to train. Okay. So there's been a lot of actually interest in this area. So how does it work? So I will basically, to explain you how it works, I'm going to have like a slide which is extremely basic. So I feel a bit embarrassed to present that in a room at Collège de France, but this is Markov chain 101, but at least it will basically introduce the kind of notation I will need for the next 5-6 slides, okay? So I'm not gonna give you any context to start with. I'm just gonna basically introduce basic concept of a kind of discrete time Markov chain living in RD, okay? And I'm gonna assume everything has density for the time being with respect to Lebesgue. Okay, so consider a discrete time Markov chain, okay? So X naught is distributed according to a distribution density P naught and evolve according at time K plus 1 according to some kind of Markov transition kernel, Markov transition density, Pk plus 1 even K. Okay? So obviously, if you want to simulate the path of a Markov chain X naught, X1, X2, Xn, well, basically you first sample X naught, then X1, X2, and X3, and Xn, and basically what is the joint density of this sequence of state? Well, it's given by this expression, simply. It's just the chain rule. Okay, good. So this is going to define some kind of forward dynamic, if you want. And I'm going to denote by Pk the marginal density of Xk under this forward dynamic. And obviously, it satisfies a very simple Chapman-Kolmogorov equation. So I can express the marginal density of Xk as a function of marginal density at time K minus 1 on the Markov transition kernel. Okay. So now assume I tell you, okay, so that's the kind of easiest way, the forward way to sample your Markov chain, okay? But equivalently, what you could have done if you are interested in sampling the sequence of Markov state from this joint density, where you could have used the kind of backward decomposition of this, essentially this density, okay? So what you say, you're going to decompose this density now, backward direction, okay? And you know it's still a Markov chain. So what it is, well, the state Xn is going to be distributed according to its marginal density under the forward dynamic Pn, and basically you're going to have a product of backward Markov transition density that takes you from Xk plus 1 to Xk, okay? Where you'll be able to express simply this backward Markov transition density using base rule, so it's going to be essentially given by forward Markov transition density times the ratio of marginal density for Xk and Xk plus 1, okay? I'll write the formula later, but it's obviously a trivial application of base rule. Okay, so basically what I'm telling you now is that if you want to sample basically some, like Markov chain path, X0, X1, a sequence of state X0, X1, Xn, basically you can use, instead of using this kind of forward sampling mechanism, which is the kind of obvious one, you could use what is now known in this literature as ancestral sampling, which is you sample at time n, Xn according to Pn, and then you recurse backward, actually, your sequence, and you sample Xk given Xk plus 1 according to this backward Markov transition density. Okay, so that's completely elementary, but that's the key idea behind this idea of denoising diffusion model. Okay, so how are we going to use that how is it related to essentially generative modeling. So the key idea is going to be the following. Think of peanut essentially as a distribution of the data. Okay? So what you're given when you want to do generative modeling, you have access, so think of images, that's going to be essentially the running example. You have been given access to a collection of, say, 100,000, 2 million images, okay? And that's going to be basically kind of the distribution of the data. So this has, this is essentially, oh, sorry. Oh no, sorry. Apologies. So you can think of this example, this image example, as some kind of empirical approximation of the true data distribution. I don't know why it's disappeared. That's not me. C'est? Okay, okay. Good, good. Yes, that's maybe because of that. Okay. So think of that as that's going to be peanut, distribution of the data. And what you're going to do essentially is that you're going to basically take this distribution of data and basically build a Markov chain, Markov transition kernel, that essentially are such that at time n, you have now a distribution Pn, which is roughly a multivariate normal distribution. So essentially, you've defined some kind of stochastic transport that takes you from distribution of the data to Gaussian distribution. Okay? So I give you here an example of one sample. So here, this is basically, I would have picked X naught from my database. I end up like, it's an image of a dog. And basically, if I simulate my Markov chain, at time n, I've got some kind of Gaussian noise sample. Okay? So that's basically the transformation you do. So you've been progressively basically taking your data distribution and transforming it according to some kind of Gaussian distribution. And now, what we're saying is that okay, so I'm going to give more detail later, but it's going to be obviously quite trivial to define such a forward mechanism. And then I'm telling you what is generative modeling is doing the reverse. You're going from essentially a Gaussian noise sample, and you're going backward to something that corresponds to the data distribution. So that's literally the key idea. Okay. I'll give you a simple example here. So this is taken from the very nice paper by Yang Song that was also mentioned by Stéphane Mallat in his first talk. So here, this is an example where you would have the distribution peanut is some kind of bimodal distribution. And essentially what you do, what I draw here basically are some kind of sample paths of realization of the Markov chain, okay? And basically, if I were to draw a lot of them and look at the histogram, basically, I would have a distribution of final state, which is roughly Gaussian, okay? So that's the way I define my forward mechanism. And really what I want to do is do the reverse. So I start from the Gaussian. I'm going to basically do mimic this kind of ancestral sampling procedure to go back to time 0 and having something that is distributed according to the original distribution peanut. Okay? So here I do it for essentially distribution on the real line, and the idea is to do that for distribution basically on the space of images, so it's going to be extremely high dimensional. Okay. Now the question is, how do we define such mechanism? Well, it's going to be quite easy to define a forward mechanism. Really, I want to basically transport my distribution for, distribution of data to Gaussian distribution. Well, I can use simply as forward Markov transition density, some kind of autoregressive Gaussian, okay, where alpha is, say, close to what? So 0.99. So, okay, so if you do that, that's a kind of autoregressive process, Gaussian process, and you know basically that it admits as invariant distribution. The Gaussian distribution is going to converge geometrically fast toward the multivariate Gaussian distribution. So you can use that. Okay? So you do that, you're going to apply that. Okay, so that's going to be a way to do the forward simulation. But remember that what we are interested in is not really to do the forward simulation. We are interested in essentially doing the reverse thing, because adding noise to data is easy, obviously going from noise sample to data is generative modeling. Okay, so what we are interested in, going to be interested is basically mimicking this ancestral sampling mechanism, which is basically this. This is the scenario where you simulate xn from Pn, marginal distribution, essentially of xn on the forward dynamic, and you recurse backward according to the Markov transition kernel. Okay? Where first approximation, we're going to say, you know, I've noised my data long enough so that basically the marginal density of xn under the forward dynamic is roughly actually a multivariate normal. So I could basically simply, in my ancestral sampling procedure, replace Pn by this Gaussian density. But, well, I mean, that's the easy bit because we still need to approximate this backward Markov transition kernel. Okay? So how are we going to do that? Well, we're going to do things in a dirty way and we'll be a bit cleaner later. Okay, so remember that we're having essentially this really very simple forward dynamic. Okay, so on what I'm interested in approximating are those backward Markov transition kernel. Okay, so this backward Markov transition kernel, I told you, is a simple application of Bayes rule. So backward is equal to forward time ratio, basically, of the marginal density at time k and at time k plus 1. Okay? And now, well, I assume essentially that alpha is very, very close to 1. So pk, okay, the marginal density pk is roughly the marginal density of pk plus 1. And so this thing is approximately equal to log pk plus 1 xk minus log pk plus 1 xk plus 1. I do a Taylor expansion, okay, little Taylor expansion, I recombine with the kind of autoregressive kernel I have, and this is the expression I obtain eventually, okay? And this is where the so-called score, or Stein score, appears, coming from, okay? So we have this expression here, this expression for the kind of backward Markov transition kernel, which involves this score. Okay, so we've made progress, but in the sense that we kind of have an idea of how to approximate this backward Markov transition density, but we are not quite done, because we need to still discover they're typically intractable. So what are we going to do to approximate that? Well, we're going to use some expression which is known in the literature somehow as score matching or denoising score matching, actually, which is the following thing. Okay, so remember that pk is the marginal density of xk under the forward dynamic, and basically I can rewrite it as p naught, which is basically transported by the transition kernel that takes me from x naught to xk. Because this transition kernel, well, it's a combination of simple autoregressive kernel, so I have an analytic expression for that. Okay, so this thing is a Gaussian density. Okay, I have argument xk, mean like some kind of parameter alpha x naught, and basically some additional variance term. Okay, so it's simple, it has a simple expression. So I'm going to use that. Okay, so now what I do, I say, well, okay, so this is a relationship for pk as a function, essentially of the data distribution on this kind of Markov transition density forward one, which I know analytically, and basically by elementary, actually, manipulation, you can find that essentially the score of interest, quantity I would like to essentially estimate, is equal to basically the gradient of the log of the transition with respect to xk, but this quantity, I can compute it exactly. And here I have basically some kind of posterior distribution, essentially, of x naught given xk, conditional distribution of x naught given xk. Okay, so we made progress, not quite yet, because, well, I don't know this distribution, okay? I don't even know it up to normalizing constant, because the only thing I have access from p naught is basically some sample. So I cannot do that, but essentially, it's a conditional expectation. So if it's a conditional expectation, essentially, you could say, well, okay, if I had access to all measurable functions, say, and I was minimizing respect, basically, to this class of function, the kind of square norm between, so S on the gradient of log transition, then I know that by definition, I will obtain the conditional expectation of interest that is the true score, okay? And here, the nice thing is that the expectation is with respect to the joint distribution of x naught on xk, or not the conditional distribution of x naught on xk. So really, what we say is that, well, okay, whenever you have a conditional, expectation, just reformulate that essentially as some kind of essentially unconditional minimization problem with respect to kind of general class of function. But obviously, you don't have access to all measurable functions. So what you do, you're going to parameterize that, you're going to restrict yourself to a kind of limited class, and we're going to pick some kind of neural net. Okay. So what we're going to do, we're going to say, okay, I'm going to parameterize by some parameter theta. It's going to be a neural net, very flexible, and I'm going to minimize basically with respect to theta this expectation, and I can do that quite easily using stochastic gradient because I have access to unbiased estimate of such objective. And the reason why I have access to that is because I can trivially, essentially, sample unconditionally of x naught on xk. I pick a sample at random in my database and I add noise to it. That's it. Okay. Because you have to estimate the score not only at time 1, at time k, but like all the intermediate step 1, 2, 3, and so on till n, what you do practically, you just have one neural net which has essentially two input, time and space, and is going to parameterize the whole collection of scores, and you minimize this kind of combined loss. And there's a lot of variants which are available in the literature. You could put some little parameter lambda k here, but it's kind of irrelevant. That's the kind of key idea. Okay, so now really that's the idea. What you're doing is that essentially you take your data, okay, you noise them, and essentially you then learn the scores through some kind of neural net approximation using a simple kind of stochastic gradient algorithm. Okay, so no adversarial training like for algorithm like GAN, which was very unstable. So there's no such issue that come when you do that. Okay, so you do that, and once you've done that, now you're in a position to mimic this kind of ancestral sampling procedure. So what you're doing, you're sampling, and the final time step, you use a sample, a Gaussian noise sample, and then you recurse backward, and you simulate xk, given xk plus 1 according to an approximation to the backward Markov transition density. Okay, so I make two approximations. One is that basically this first approximation, and because I do not even have access to the score here, I replace that by my neural net estimate. And here we go, I go till time 0, and I've got a sample. So this is what people are doing. Okay. Okay, so if you write that in continuous time, it's actually a bit neater. Obviously, the following. So you can think that really what this kind of forward noising mechanism I've been defining is doing is simply that essentially you define what I was doing. I was discrete time, but what the discrete time process I defined is just a discretized version of the Einstein-Lengbach process that is initialized at the distribution of the data. So this is your forward, basically, diffusion, okay? And really, what you want to do, if you wanted to do essentially ancestral sampling, what you would do, you would sample from the time reversal of this diffusion. And the time reversal of a diffusion is also a diffusion. And I've written this expression here, and what we have that appear in the drift, well, we have the scores, okay? So that's the time reversal, so that corresponds essentially to the exact ancestral sampling. And once more, what do? Actually, I make two approximations. I don't initialize this time reverse diffusion by the exact marginal of xt under the forward diffusion, okay? Because this thing, well, I don't know what it is, so I'm going to replace it by some kind of Gaussian, because I know it's close to a Gaussian. And the second thing is that basically here I will plug some kind of neural net approximation of the scores, okay? So basically I will define the time reverse the approximation of a time reversal I'm going to consider is a diffusion which starts basically according to Gaussian and run according to this dynamics. Okay. So now how do you train, the way I was showing this expression previously, that I had shown that, well, you could come up with an estimate of the neural net by looking at looking that the score could be formulated as a kind of essentially conditional expectation, which essentially could be approximated by some solution to a regression problem. Well, alternatively, maybe much simpler, you could say, well, if you have a generic, some kind of parameterized diffusion with a score as theta, well, what do you want to do? You would like to find theta such that the induced path measure Q theta is closest to the true time reversal, okay, in terms of Kullback-Leibler discrepancy. And it turns out that when you look at this simple expression, this Kullback-Leibler discrepancy, and you want to minimize it with respect to theta, it's equivalent to minimize this expression, which is exactly the kind of continuous time version of what I'd done before, okay? See the magic again. The magic is that basically, if you are just doing a little Gersanoff here, you would have the intractable score that appear by using this kind of score matching trick. Now you just have the transition kernel of the Ornstein-Uhlenbeck, which is a tractable quantity. Yeah?
So here, this P is the path measure of the reverse.
Yeah, this is yeah. Okay, so there are convergence results. I'm not even going to talk about it. We have Valentin, the specialist in our room. So in the paper, Valentin is the first one, I should say it, I should advertise it well. Valentin is the first one who proved essentially a theoretical result on this class of model, obtaining a bound basically on the total, a bound on the total variation between the true distribution of the data on the law of this kind of approximate time reverse discretized diffusion, okay? The results are much better now, okay? But what we say, in particular in this paper from a month ago, and have been superseded by a paper from MIT last week, but it's a fast-moving area. But there's something maybe I should emphasize, which is actually, I think, quite nice, is when you run those algorithms, you know, we had a lot actually of question at the beginning when we started working on that. When you look at this kind of, you're going to run practically some kind of time discretized version of this diffusion, on essentially it mix. Essentially you pick two Gaussian samples, you run it on it sample very diverse images. Or you could say that's a bit strange because, you know, I mean, I've done a bit of Langevin, nothing as much as Alain, but a bit, and I know that shouldn't really mix very well in for complicated multi-modal targets. So why is it the case? And somehow it's the case, and this is a gross oversimplification of really what's going on. But it is the case because some of the time reversal you're trying to approximate has itself extremely good mixing property because it inherits the mixing property of the Ornstein-Uhlenbeck process. So somehow we don't have really any mixing problem. So that is actually quite nice about it. Okay, so that's nice, but there are limitations, okay? And one limitation, which is key, is that really, so we are having like, basically I told you what you need to do. You really need to kind of diffuse slowly to a Gaussian distribution, okay? And then when you're done, when you learn the score for this forward diffusion, each time you want to generate a sample, you basically start from a Gaussian noise, and progressively you get back to time zero. What it means is that simulation to obtain sample, it's quite costly. It's essentially n times more costly than the simulation for GANs, to simplify, okay? So obviously, what would be nice is not to have to diffuse. So I'm here, I have an example in 2 dimensions. We like to kind of use like your Ornstein-Uhlenbeck, not diffuse too much. Or maybe if you were time reversing, obviously, then it would be giving something close to Gaussian. Obviously, it doesn't work. Okay, so there's no escape. If you really want these kind of techniques to work well, you need to have moved towards something that is roughly Gaussian, and it means that the cost to pay is that the backward simulation takes a long time. Okay, so what can you do? Well, you can try to reformulate this kind of generative modeling problem as some kind of so-called Schrödinger bridge. Okay. So Okay, so I'm going to write everything in discrete time. So I'm going to call P my best process, which is just essentially this kind of joint density of the forward noising process. So this is P naught times the product of this little autoregressive kernel. Okay? And what I'm saying is say, well, okay, what would be nice is that if I could find somehow the distribution on path space, which is closest to this base process, okay, P, in terms of KL, with two additional constraints. Okay, so I'd like its marginal at time 0 to correspond to the distribution of the data, and I'd like its marginal at time n to be basically exactly equal to a Gaussian distribution. Okay, so if I could find that, if I could find basically such a process, let's call it pi star, then I could do ancestral sampling from pi star. So what I would do, I would sample xn from its marginal at time n, but by construction, because pi star satisfies this condition, then I know this marginal distribution at time n is exactly a Gaussian. I will recurse backward on essentially at time 0. I know I would have sampled from the data because by construction, similarly, pi star at time 0 is correspond to the distribution of the data. Okay? We're not going to have time to discuss that, but you could say trying to solve this problem, if you had some kind of forward noising process that was not autoregressive, but simply some kind of simple Brownian motion, it corresponds to solving an entropy regularized version of optimal transport. Okay? And we are specialists in Paris, aussi Marco Couture and Gabriel Perret, but they work typically essentially with finite measures. So here the idea is basically to move to kind of continuous state space. Okay, how do you solve that? Well, the first solution to this problem, at least formal, was proposed, as far as I know, by Robert Forte in 1940. And this is an algorithm that has been rediscovered over and over in the literature. So in particular, by Kullback in 1968, and I think he is the one who introduced the term iterative proportional fitting, but I might be wrong. And when you're dealing, basically, we're doing linear algebra, is the correspond to the kind of synchron algorithm. Okay, so how much I have left?
10 minutes.
Okay, good. Okay, so what does it do? So it's an iterative algorithm where you only essentially enforce one of the constraints, distributional constraint, at each iteration. Okay, so at all iteration, you enforce that the marginal at time n correspond to this Gaussian distribution. At even iteration, you basically enforce that the marginal is distribution at time 0 corresponds to the distribution of the data. And you know that it converges under fairly weak regularity condition to the solution of Schrödinger bridge. There's a long history, many results on this topic. Okay, so now how do you do that practically? So maybe we can see a bit the structure of the iterates. So let's start basically the first. We initialize this recursion using the reference process. So when we want to solve the first iterate, well, what we have, I say, we want to minimize the scale with respect to pi under the constraint that the marginal at time n is the distribution, the Gaussian distribution. Well, it has a simple expression. Essentially, by hand, you write it, that what it is the kind of joint distribution, okay? Time n is distributed according to the, essentially, Gaussian. On essentially what you do, you add the forward dynamic and you take, essentially, you define the backward-backward transition kernel associated to pi 1 by essentially time reversing the dynamic of pi naught, which is p. So what it is, this thing, well, it's exactly what we're doing where we're doing standard denoising diffusion model. Okay, so the kind of key thing, you can think as denoising diffusion model as essentially the first iteration of this kind of iterative proportional fitting algorithm on if basically the marginal distribution of xn under the forward dynamic is approximately Gaussian, essentially you've converged. You don't need to iterate. Okay? But if it is the case that P Pref is very different from the marginal density of Xn and the forward dynamic Pn, then what you do, you iterate. So second iterate, well, the second iterate, I enforce this time the marginal at time 0. I have an explicit expression, and essentially what it is, it's a forward process which is initialized at the distribution of the data, and its forward dynamic is obtained by time reversing, essentially the dynamic of pi1, and so on and so forth. Okay? So you can write that essentially in continuous time. So what you have is that at even iteration, you have naturally some forward diffusion which are initialized at the distribution of the data. On at odd iteration, you have time reverse diffusion which are initialized at the Gaussian distribution. And you have a relationship basically between the drift at between iteration. This recursion involves the score of either the previous forward process or either the previous backward process, which you can again estimate using the score matching idea. So I'm not going to repeat that. So I give you here some illustration. So let's pick this kind of 2D, simple 2D dimensional distribution. And let's make sure that we define a forward dynamic which is such that essentially I am not anywhere close to a Gaussian at time n. Okay? So if you do just one step of IPF, it corresponds to doing the standard denoising diffusion model, on what you obtain at 0 is something that is nothing like the distribution of the data. And here, if you do 20 iterations, we see that we recover actually the distribution of the data quite well. Okay, so we have more examples. So this is not the most impressive visual experiments. We had a 1,000 pound budget, so I think we're kind of a bit forgiven for that, and it's about more than a year and a half ago. It got better now. But basically, you're able to simulate at a time in a fairly short step, number of steps, actually fairly good quality images. Although that was pretty small at the time, but it's improved everything. So that's yet another way to improve this kind of score-based generative model. Okay. What you can do as well is you can do things like interpolating between two empirical distributions. So what I've presented here is basically in the framework of generative modeling, but there's no reason you can use this algorithm as kind of broader, much more applicable than that. In particular, yeah, you can interpolate between those empirical distributions. But perhaps what is more important for me, I'm in the stats department, is you can do inference as well. Okay? So for the timing, it's just essentially simulated fake image or, done things like that, but that's not really what I'm interested in. Okay, so typically what I have, I've done a lot of Bayesian computation. You have this kind of prior, you have some kind of likelihood on some of an observation y-ups you like to sample approximately from the posterior distribution of x given y-ups. Okay? Where obviously, clearly, we are not going to be able to do directly to apply those techniques. So what people have done, maybe it was 1 year, 2 years ago, what they used to do is that somehow they would learn the score of the data. So you don't have access to PX, to the prior, but you have access to the database. So what you try to do, you use basically, you learn the score of the prior, so grad log P data using some kind of score techniques, and then you would plug that in some kind of Langevin algorithm and combine that with the likelihood term so as to do MCMC. Problem is that you end up doing standard Langevin MCMC, doesn't really mix very well, so is it possible to do something which kind of somehow completely bypass having to do normal MCMC? Okay. So is it possible to, well, we could say, okay, we could try to instead try to use this kind of Schrödinger bridge idea with on new algorithm we've developed before, and basically instead of having as a constraint essentially the data distribution, we would have the posterior distribution we're interested in. Okay? And we would like to use the algorithm we've been developing before so as to actually approximate the solution. And then whenever we want to sample, you could try to do that, but it makes no sense. So why it makes no sense? It makes no sense because the algorithm I've presented before, it requires you to be able to sample from the terminal condition. And here, one of the terminal conditions is the posterior distribution I'm trying to sample from in the first place. So naive application of that doesn't work. We don't have much time, so I will go quite quickly. But essentially, there's a way to get over that, which is by essentially using a Schrödinger bridge in an extended space. So essentially, you're going to define a Schrödinger bridge between the joint distribution of x and y, which you assume you can sample from, on some easy to sample reference distribution, which is here essentially some multivariate normal, say, time the marginal distribution of the observation y, which you can also easily sample from. And I'm telling you that if you're able to build a Schrödinger bridge between these two distributions, then essentially it's a straightforward, basically, straightforwardly you can sample from the posterior distribution of interest. Okay, so I leave it to you. We don't have much time. So I give you here an example which is for image super resolution. So this is an example for Celebi. So this is the ground truth. Okay, this is some kind of corrupted image. And basically what I say, okay, so I've learned one single neural net. It's not for each individual image, it's going to work for all images which is corrupted. Then I basically give y-ups to the kind of, essentially, the kind of score network I've learned. I simulate a reverse diffusion. After 20 time step in this case, I have an approximate posterior sample. If I rerun it, 20 time step, I've got different, like, this is essentially each time a different posterior sample. So this example is actually the kind of perhaps the most interesting one. So this is the information I have access to. And you see that basically the sampler, sometimes you say, okay, this person has no glass. Maybe they have glass, actually. And you can sample here like that. And it's 20 iterations. This is in about 116,000 dimensions. If you could not do that with MCMC, it doesn't mix that well. Okay, so that's an application. Do we have 1 minute? This is for Marilou. I promise, Marilou, I will talk about standard Monte Carlo sampling using score-based techniques. Okay, so I'm just going to write a slide. So everything I've done is this kind of generative modeling. So you do generative modeling or approximate posterior sampling, essentially. Now, I tell you, okay, is it possible to use that in a context where I give you some kind of general distribution pi of x, which is of the form gamma x of the z, kind of intractable normalizing constant, and what I want to do is estimate the normalizing constant. Okay, so in statistics, and actually in physics, a very standard technique so as to do that is this kind of Jarzynski-Crookes techniques, also known in statistics as annual importance sampling, where basically you define some kind of sequence of temperate target distribution. So at the beginning you start with really something which is really temperate, so it mixes quite well if you use Langevin, and then you temper that toward basically pi. What you could do, you run some kind of non-homogeneous forward diffusion, okay? And then when you're at time capital T, you have something, it's like doing simulated annealing, it's roughly a sample from pi, okay? But not, because your Langevin diffusion has never been at equilibrium. You basically just run that in finite time. Essentially, what you want to do is to use some kind of impedance sampling correction so as to compute an estimate of the normalizing constant, okay? So what people do, well, okay, they cannot compute in closed form the marginal distribution of xt under this non-homogeneous forward Langevin diffusion, okay? So they cannot really do impedance sampling on the marginal space, so they do impedance sampling on part space. And so as to do that, you need to introduce some kind of auxiliary target distribution, which is some diffusion that finish at time t exactly according to pi, and you need to give it some kind of backward somehow dynamic so that randomly coding is well defined. And there's a standard recipe to do that, and this is the kind of Jarzynski-Crookes AIS type recipe. And what I'm telling you is that it's not optimal. This recipe is not optimal, And we had actually this result in the paper with Delmora a long time ago, 2006, tell you, well, that's not what you should be doing, actually. The way people are doing it is actually problematic, and really the way you should define this kind of extended target path measure, it should be done by basically defining a measure which essentially has a finite time, basically distribution pi, and that use as a dynamic the time reversal of the forward dynamic. And if you do that, your impedance sampling is like you're doing impedance sampling of marginal space. Obviously, this is completely impractical because you have the score, but now I know how to do score matching. So I can basically come up with a much nicer approximation of this kind of better approximation of the kind of extended target, which provides me, which return lower variance estimate. Okay, so that's about it. So just to discuss, so there's really nice class of this kind of denoising diffusion model. I think it's really exciting time actually for people like me who've been working on Monte Carlo computation, on Bayesian statistics. It opens actually kind of a lot of, there's a lot of problems we're stuck on for many years, and now I realize, oh, using those ideas, you can really move forward, and it's really nice. Whether you're like more methodology or theory person, there are enough open problems for everybody, so I think I really recommend it's a very exciting area. You can basically try to extend those kind of concepts to kind of different space. So we did it for discrete state space on Riemannian manifold with Valentin. If you're interested in reading about this kind of domain, before recommending my own paper, I would recommend the two kind of like seminal paper, I would say, in this area, which have been basically developed. So it is kind of like the kind of key paper in this area, and then with the list of our contribution. Thank you.
Thank you, Arnaud. That was not 1 minute, but maybe we have time for one.
Sorry. I wanted to talk about the AIS thing.
So, yeah, maybe one quick question.
Yeah, so maybe one question is, you never discussed about the impact of the choice of capital T or capital N.
No, we don't discuss.
In all this stuff,
No.
so I guess there is a big influence.
Yeah,
in practice.
Well, yeah. Maybe even Valentin cannot say this. For example, it's clear you cannot pick T too small when you are running the Schrödinger bridge, because if you had to do that, then you had your score becomes very steep, and then your drift becomes very steep, and obviously numerically it's not going to work well. So some has a bit of empiric, so that its T is like kind of large enough, so that essentially the kind of diffusion in this case the diffusion you need to approximate don't have actually scores that are too steep. And then there's a lot of trick as well. So for example, when you do this conditional simulation, I don't have it here. What you're going to try to do is you're going to try to diffuse to distribution, which are not a simple, say, normal, but is going to be informed by the data. So that essentially you reduce the kind of discrepancy between the distribution you're interested in sampling and the reference distribution, and it helps a lot, obviously, your numerical algorithm. But I don't think this thing has yet been very formalized. It's true, yeah.
Okay, so let's thank Arnaud again. And,
you.
So yeah, just two free announcements before we start. So you must have received an email by Marilou. So if you are a speaker, could you put your slides into it's a Google Drive, right, Marilou? Yeah. So the link is in the email. Second information for those who are coming tomorrow, the meeting is at 9 at ENS, so right down the street. So there will be some, like one of us will be here to wait for you, and there is our phone number as well. And what was the, yeah, no, I think that's it. I think there was only two announcements, yeah, sorry. Okay, so now we're going back to generative modeling and generative modeling of protein sequences with Martin. So the floor is yours.
Okay, thank you very much, and thanks for the invitation to speak here. So it's a talk which is a bit off track for compared to most others, because what we do methodologically is not super sophisticated as compared to many things we have seen, but we are working with real protein sequences, and at the end there is some experimentalists trying these protein sequences in real bacteria which have to live with it and so on. And so it's kind of a different type of complication than as compared to most of the talks. So just to give a short introduction, because probably many of you don't know so much about proteins. Proteins are super important in biology, because they are kind of the workhorses in the cell. They do multitude of function. They are enzymes, they are transporters, they are important for the structure of cells, they are important for cells talking to the environment via some signal transduction. They make proteins, they make RNA, they make DNA, they make everything. So these are the machines, molecular machines. And in principle, they, in the first place, they look very simple, because they are, in the first case, linear chains made of amino acids. And amino acids, there are 20 natural amino acids. And these amino acids have very, very distinct physical and chemical properties. You see here that some are positively charged, some negatively, some are small, some are big, some are hydrophilic, hydrophobic, and so on. So they have a lot of properties, and according how to you put them into in this one-dimensional string, in this sequence of amino acids, you will get very distinct objects. Actually, if you put them randomly in a kind of random heteropolymer, this will not look like a protein. Will be, I don't know what it will do. But a real protein folds into some kind of hierarchical structure with some local structure like alpha helices or some extended strands and so on. These fold into three-dimensional structure, mostly into some relatively global object, globular object, relatively compact, not always, but in many cases, or maybe even several proteins interact and form a complex to have something more bigger and more complicated. And these structures here are built upon these structures, tertiary and quaternary structure, because most of these functions are realized via some of the amino acids which are exposed in the surface of the protein, and they have to be exposed in some very special spatial arrangement. And so the faithful folding into a well-defined structure is essential for the function. So if you want to understand function, it's nice to understand structure, but actually if you look to experimental data, there's very little of it, while there is very, very much about sequence data. And the reason is very simple, that in the last, since 2007 or so, we are able, or some people are able to sequence very easily big amounts of genomes. And once you have a genome, that's a DNA sequence, it's relatively easy to identify where genes are and to use the genetic code to translate it into these linear sequences. But this is strings of letters over this 20-letter alphabet here, and not more than this. While this one here requires typically very detailed experimental work on an individual protein. You have to express it somehow. You have to get enough of it, you have to purify it, you have to maybe, most structures are for instance by X-ray crystallography, so you have to crystallize it, which is something which proteins not necessarily like, because they like to be in solution and not in a crystal and so on. And so this one is a lot of annoying work. Getting one of this is sometimes more than a PhD, and sometimes a PhD student manages to get 2 or 3, but not more than this. So just to give you an idea about what I mean with many abundant data and not abundant data, this is one of the biggest protein sequence database, UniProt. And you see this is size of the total database. It's basically growing exponentially up to here they have reorganized the protein database. That's why there is a drop. But then they basically have reduced some redundancy here. But you see it's basically an exponential growth. We have more than 200 million proteins now. But these are sequences which come from these DNA sequencing without, so these are just these strings of these 20 characters. Whereas we have a sub-database which has the proteins which have so-called manual annotations, and these are results of experiments. So this might be the structure I have talked about. So might be, for instance, some crystal structure or some MNR structure, or some cryo-EM structure or so, but it may be also some functional assignment that you know this is an enzyme catalyzing a certain reaction or so. But you see this one is line is really flat, which doesn't mean that this information is not increasing. The information is getting better and better for the same proteins, not for more proteins, and that's something which is based mostly in the way how biologists work. They like to work on proteins coming from so-called model organisms, which is like E. coli as a model bacterium, or Salmonella, or Bifidobacter or so. And then for eukaryotes, it's yeast and some worms and some flies and us and rats and so on. So these proteins basically come from a few organisms and are better and better characterized. And why not more organisms? Adapting the biochemical protocols to a new organism is a lot of work, takes a lot of time, and all this time is not producing any result, so it's kind of complicated. So really building up the protocols for a new model organism is very complicated and costly in time and in resources. So now you see we would like to know also something about these proteins, and so you can ask many questions. You can look to these ensembles to do some unsupervised learning. You can try to do some supervised learning with this one here. You probably all have heard about AlphaFold last year, which basically learns from, gives us input this kind of data, and is supervised with structure and can predict structure in a way which was believed to be unreachable for a long time. Okay, so what I'm going to talk about is so-called protein families. These are typically very small subsets of my big database. Something like typically of 1,000 to, in few cases, 1 million sequences, but mostly a few thousand sequences. And they are they share a common ancestry in evolution. So they come from some common ancestor, which was basically in some ancestral species already doing the same thing. So having fulfilling the same function, having probably a very, very similar structure and so on. Obviously, we don't have this ancestral because it lived sometimes 1 billion years ago. But we can find its grandchildren in different species, and can build up these protein families. And since each of the extant species needs this function, these proteins which we find there are functional and have the very, very conserved function, very similar function. Structurally, I said that function is built on structure, so also structurally they are very, very similar, but they are very diverged in sequence. Over time, they have accumulated in more than 70–80% of the positions. They have accumulated mutations changing amino acids, so they don't look very similar. It's better than random because we have 20 amino acids, so the random sequence would be have 1 over 20 would be 5% identity, and these have 20–30. But still, if you take any of these proteins and you introduce, say, 10 random mutations, you will blow it. It will be, it will not function. And here they accumulate in some cases hundreds of mutations. Not this one because these are relatively short. Okay, you can get these families in the form of a multiple sequence alignment, and here I have shown a part of a multiple sequence alignment just to tell you what this is. So each line is one protein sequence, and it's aligned in a sense that these protein sequences look as similar as possible. And you see that there are these little minuses. These are what is called alignment gaps, because proteins in evolution can sometimes gain a few amino acids, they can lose a few amino acids, and so they are not all of the same length, even if they do the same thing, if they fold into the same thing. And there are procedures which we built upon, which are able to construct these alignments. And for instance, here you see this alignment here has done one column which is all H. Actually, the protein is called histidine kinase, and histidine has the letter H. So if you change this one, this protein will be dead, because this is what is called the active site of this protein, and you need to have it. But other columns here, like this one here, look quite much more variable. Okay, so what we have is we have thousands of sequences which are diverse between each other, but which are kind of solutions to the same functional task. So to do something with these, we learn statistical sequence model. So these for each family there is one model. So if we have many families, we have many models, but each family has one model. And this is basically a probability of one of these sequences. Provides a probability to any sequence, and you can visualize it as via some kind of statistical energy or negative log probability. So this is not an energy in terms of kilojoule or so, which is constructed from some first principles or so. It's something which we learn from here. So it's just a minus log probability, but it's practical to visualize in this way, because like this you can imagine that good sequences are kind of low energy, so high probability, and bad sequences are those which are of high energy. We learn by maximum likelihood. Actually, we tweak our model that actually these ones here are basically at low energy. Okay, so that's first thing we do. So we have some kind of landscape, and already this one allows us to do some interesting biological predictions. For instance, if I take a sequence and now I introduce a mutation, so I change one position, one amino acid, then either this energy will go up or down. And I would say if it goes up, it's probably a deleterious mutation, so not a very good mutation because the probability goes down. Vice versa, if it goes down, maybe it's a beneficial mutation. If this happens, probably I can hopefully predict or quantify fitness and selection on proteins, and maybe I can even forecast protein evolution. I will show you examples. But what is kind of non-trivial in here is that these sequences which we have taken here, they come from very broad range of species. So they are representative for hundred of million, billion year of evolution. And the single mutation, that's something which is comparable to 1 year. So remember about SARS-CoV-2, all the variants. The frequency variants appear as something which tells us about how frequent mutations are in viruses. They are faster than in other organisms because they have less mechanisms to repair errors, but okay. And obviously it's not so easy to put together 9 orders of time scale. So if we did well our model, or this is a model, the statistical model, so in principle I can sample from them, and I don't care how to sample. I just say, okay, if I can sample, if I get an IID sample from them, then these are maybe other nice sequences, and I could ask myself if my sample is actually real proteins. Okay, so that's what we had. So if I talk about generative modeling, it's a bit easier concept, or a bit different at odds from, for instance, what Marie-Lou said this morning, because what I just say is, if I sample, then my sample sequence should capture the statistics of the of the natural sequences. Whatever this means is not very well defined. But I'm a physicist who moved to biology, so don't expect me to say anything well defined here. But they should also be diverse in sequence, because I don't want to copy these ones. I want to have other sequences which are as good as the natural sequences, if I can.
Sorry, can I just, maybe I missed why you want these other sequences, these artificial sequences. Did you already answer that?
I did not yet answer. Here I say just if I can, it's fun for me because I can change. But protein design and protein optimization is something which in terms of biotechnological applications is super important. And there is something which for me is actually more important. If I manage to have a model that these things are actually functional proteins, then probably my model captures important biology. And actually, I keep my models voluntarily very simple as possible, to still have something which is good sequences here, to make them interpretable. And so I learned something about maybe what is happening in evolution and so on. And you will see a few cases in examples. So it's not so easy because data are quite high dimensional. So the sequence spaces we are talking about are big. Typical proteins have lengths between 50 to 500 amino acids. So for each family, it's better defined. This is different families have more. My data are quite limited, and I don't know what these actually is, because I don't have any first principles to write down. So I need to invent some models. And the models I invent, I think they should respect at least 2 biological observations. So they should be biological sensitive. The first one I already discussed is these conserved columns. So there are some residues which never change in evolution over 1 billion of years, and there is probably a reason for this. So I should rather not change it. So this can be statistically captured by, oops, no, this was the wrong button. 4 buttons is too much for me. Can be captured by just the empirical frequency of amino acids in each column. So this would be 100% histidine in this one, but the others are more mixed. But there's something else. Since I talked about structure, I will have amino acids which are quite distant along this one-dimensional string, which come together. And they really form physical contacts, and not all pairs are equally good as in contact. For instance, I talked about charged, and you have probably heard about Coulomb interaction. It's not so easy to put 2 equally charged amino acids together, and you find not so many together in structures. So probably also the pair distribution. So if you look 2 columns, it will frequently be correlated, not just factorized in the individual, because certain combinations are not good and other combinations are better. This is what is called coevolution, and this is what is called conservation in biological terms. And I would claim that any good generative model needs to capture these effects. And actually, in particular, coevolution has reached some certain status of interest in computational biology, because coevolution is the basic signal which is used for protein structure prediction, including AlphaFold. AlphaFold detects coevolution via some attention mechanisms which are deeply built into the model, into the transformer models which are at the core of AlphaFold, but they detect exactly this coevolution signal. So just remember that coevolution can be used for structure prediction. How this is done, don't care, but it can be used. We will come back to this one. Model architectures are frequently quite simple in our case. We used a lot of Boltzmann machines or Potts models or Markov random field, where you don't have any latent variables, or so you just try to model these single. So you just try to reproduce these single site statistics and the pair statistics. It's a sufficient statistics for this kind of model. We use restricted Boltzmann machines. We use some simple autoregressive models. There are deep generative models which are used, but so far none of them is really convincing in the sense that they outperform very simple models. This is probably due to the fact that for the individual families, data are still relatively limited. So you have something like 1,000 sequences, and very complicated models don't perform better than simple models. Maybe in the biggest, there is a slight tendency that in the biggest families, maybe they work a bit better. Okay. So, I told you about these mutational effects. And biologists nowadays are able to do really magical stuff, magical experiments. And one of these magical experiments is what is called deep mutational scanning. And this is here, this is my protein. These are the positions in my protein. It's a protein of length 200 in this case. And what they do is they take the sequence, and each individual amino acid is replaced by all the 19 possible other amino acids. So each point here is one experiment. So this plot is 4,000 experiments. And you measure the effect of the fitness, on the function of the protein. So the blue ones are deleterious mutation, the green ones are beneficial mutation, and these red dots is the original sequences. This can be measured. This last 5 years about. We can predict it, and we get here, in this case, a quite good correlation, 76%. You see the structure of these two plots looks quite similar.
Just a clarification, when you say it can be measured, it's actual real-world experiments?
It's real experiment. So this is real experiment, this is our prediction, and this is a correlation between them. This is actually one of the best proteins. Yeah, hardly so good, but it's related to two facts, because we have good alignments, so we can learn good models, but also the experiments are done on something which is really a proxy of fitness, so which is what is the selective force in evolution. Sometimes experiments are done on binding of some molecule and so on, and this is not necessarily very related to what is shaping the variability of my initial data. Okay.
Just for my information, is this done on an organism? So this is in E. coli or something?
This is in E. coli. So this is a protein which is called TEM1, which is providing antibiotic resistance against beta-lactams, which is amoxicillin, ampicillin, and so on. And it's one of the most successful proteins in the last 50 years. It's not in the genome of E. coli, but it's on a little plasmid. So there's a little ring of DNA. And it was found, I think, in the 60s for the first time. And at this time, a very small fraction of all E. coli bacteria had this. You know, E. coli is a super abundant bacterium. Everybody has a lot in the gut. If you take a piece of earth outside, you find a lot and so on. So they are everywhere. And very few of them had it. Now much more than half of them have this plasmid. thanks to us playing a lot with antibiotics. Okay, it's one of the most studied, experimentally most studied proteins in this case. But this is real, so this is real growth. These things here are how well it grows on antibiotic. Okay, so we can do this, and but now you can imagine that so there are some positions where this is rather white here, and white is no effect on fitness. It's a neutral mutation, and others are super blue, so everything, whatever you do, is really bad for the protein. So now you might imagine that using this you can actually predict mutation, because it might be much more easier to get a mutation in a position like this one here than in a position like this one. Let's look if this is the case. To do this, we have compiled a database of 60,000 E. coli strains. What the strains are individual E. coli which are sequenced. So it's like making sequencing each one of us. Each one would have be an own strain, but in bacteria it's called strains. And you have 60,000, so there is a lot of little sequence variability. Typically something very few percent, so something like 2%, 3% of sites are mutated. So they are very similar, much more similar than the sequences I was talking about in the beginning. But they have a few mutations. And now we tried with our model to evaluate these mutations. And here I have 3 histograms. The first histogram is random mutations, if I would introduce random mutations, and you see that they are centered in some positive value. Remember, this was energy going up is deleterious, so most of them are actually deleterious, and that's quite true. But if you look to the existing one, which are observed, they are much more concentrated around 0, and they are much more neutral. So it looks as if we could actually identify the possible mutations by predicting, okay, we take the neutral ones, the ones which don't have a large effect, as the ones probably emerging. Okay. Doing this, we have tried to predict mutations in SARS-CoV-2. And our question was, what can we predict at very early stages of a viral outbreak potential mutations in viral proteins which might emerge in viral variants? So that's a long sentence, but you have seen a lot of variants emerging, and they have mutations. Some of them became quite famous because they are immune escape mutations or so, and they are responsible for the success of some of these variants. And, but we didn't know these variants in the beginning, obviously. So what we had in December 2019 was one single SARS-CoV-2 genome coming from Wuhan WHO1. But we had big databases which contain a lot of other coronaviruses. So we can try to construct alignments. These alignments are really, really bad as compared to what I showed you before. Still, there are alignments. We can learn something. We can try to do some predictions. And what we and why is this interesting? Now a question of why interesting. If you can actually predict which sites are very mutable. So what might change a lot? You would like to avoid these sites in, for instance, vaccine design or in antibody therapies, because with these therapies or vaccines, you would like to target sites which are not mutable, because the virus wouldn't have the chance to escape. So in principle, this can be interesting. Obviously, we were a bit late in with our predictions because we had the idea. Actually, what is nice, because that this virus was mutating and so on, and we were accumulating data, and also after our prediction, and so we could check a posteriori if our predictions were okay or not. And this one is actually shown in this plot here. So it's a ROC curve, which random prediction would be the diagonal, and the perfect prediction would be vertical, horizontal. And you see here we have extracted from an existing database at different times. And if you look, the first extraction was in July 2020 when there was still very few data around. And you see it's basically like random. Why? Because the virus just did not yet explore the possible mutations. Then it started to mutate more and more and more, and you see the curves get better and better. And actually the last curve is after our publication. So a prediction which works even after the publication is kind of, anything which is in a publication is can be under doubt, but this was after the publication. And what is interesting, so what we predicted actually is not something which helps SARS-CoV-2 to be better in, I don't know, attacking us, binding to ACE2 to the human receptor, because most coronaviruses which were in our database don't bind to anything like ACE2 or ACE2 homologs and other. But what we can say, what are mutations which do not destroy the proteins of the virus itself? So there might be mutations which just invalidate the protein and then it cannot do anything, not even binding. And this is what our prediction says. And here we have a mutability score, which means these are the most mutable and these are the least mutable. You see most of them are not very mutable. And we have paired this with what is called immune response frequency, which is an experimental measure which tells us how immunogenic certain positions are. If you want details, I can tell you, but not now. Basically, is these points here are potentially immune escape mutations because they are very mutagenic according to our prediction, and they are very immunogenic according to experimental values. So we find a certain number, and if you see this is Delta, which has one single mutation in here. This is Omicron, which has 4 mutations in here. And actually, this is a significant enrichment in here. And if you look to, this is the first Omicron variant. If you look to other Omicron variants, they have, I think, still picked up 2 more out of these. So kind of, we shouldn't have told the coronavirus to make these mutations, but it did what he told him. Okay. How much time have I?
missed something. It's mutations that are in Omicron, which is there.
So the blue, I should have told you, the blue dots are what the possible, all the sites in what is called the receptor binding domain. So this is the part which docks to ACE2. And the red ones are those which are mutated in Omicron or in Delta. So Delta had 3 mutations in the receptor binding domain. This has something like 20 or so. I don't remember the number. So you can count the red dots.
So you don't like red points which are not in your red square?
So I don't, but I'm, this is, for instance, look at this one here, 331, 333, 335. They are very close to each other, and we are kind of bad in predicting them. But our models are really, we have very bad data, and maybe there are some mutations which might appear, but which are not seen by the data. This is basically mode exploration. So no, not exactly, but what we don't see in the data, we can't predict. And the data is different coronaviruses. It's not SARS-CoV-2, but still, if we don't see any variability there, we wouldn't expect any in SARS-CoV-2. But this may be wrong. So it's really we fight with super limited data there. So when we started this, I wouldn't have expected anything like what I'm showing you. It's working better, much better than I expected. But Sorbonne University gave me money, and so I could, I don't know, probably you got also money from Sorbonne University.
Just a very quick question. These amino acids, are they the codes of the mutant or of the original?
This is the original. Actually, since we have very bad data, our prediction for individual mutations, so from, I I don't know, E484R or so. Yeah. They are really bad. But what we can predict is kind of the mutability of a site, because this is already an average over 20. And averaging many noisy numbers, typically, if there's any signal, the signal gets a bit clearer, no? So it's for this individual ones, it's not good. It's really not good. For the individual mutations, we have a 50%. There are some deep mutational scanning experiments. We have something like a 50% correlation, which is for really doing prediction. So it's correlation, but for really doing prediction, 50% correlation. If you just make a scatter plot, then it looks like not super nice. Okay. Where am I in time? So I'm 5 minutes. So I skipped this part, which I knew I would have to skip, because I think this part is interesting. So what I told you is, okay, we can generative models. In principle, we can sample from these ones. And what we can do is actually we can take something which is important for E. coli, and these are E. coli bacteria here in my picture. And we can take the gene which is in E. coli, we can cut it out, and we can replace it by a gene which is either coding for something which is in another species. Not necessarily if I have something in a species which is distant, is working also in E. coli under the specific conditions in E. coli, but all of them would in principle be good sequences, or I can introduce my sequences. So I can retranslate, inverse translate my amino acid sequence into a nice E. coli gene and can put it there instead of. And then I can look how fast my bacterium grows. We sequence before and after growth, and then we just look how frequently finds the sequence after growth as compared to before growth, and we compare this to how the wild type, so normal E. coli does. So if this number is positive, it would be grow faster than E. coli, which we basically never find. But if it's very negative, we know that the protein does not work. And we can do this, and we have tested the natural sequences. And you see that about 1/3 of the natural sequences put into E. coli make E. coli grow under some condition which is where this protein is essential. So it's a protein which is a biosynthetic protein which produces 2 amino acids. And if E. coli doesn't have these amino acids, it needs to produce it on themselves. And if it cannot produce them, it cannot grow. So if it's growing here, it means that this protein is working in vivo in the beast. 2/3 are not growing. These are our sampled sequences, and we have voluntarily sampled over a larger range of energies. So this vertical axis is our model. And you see whenever they have too high energy, they are never functioning. But actually, these ones are functioning. So there are many functioning. And what is quite astonishing is that these, remember, are things we learn. A Boltzmann machine, a POTS model from 1,000 sequences. We make some MCMC from these to find something which is at many mutations away. We put it into E. coli, and this thing works. So this is quite astonishing. In particular, if you look to some numbers of how big these spaces are, so 20 amino acids, length 96, this is 10 to the 124 sequences, which is quite a number. If you just look to conservation, so like this blue column histidine and so on, if you impose this one in a simple model which in physics language would have local fields but no interactions, you would still have 10 to the 86 sequences. If you put the model which has also coevolution, so which has in this statistical physics language fields and couplings, this would go down to 10 to the 54 sequences. So a random sequence we would estimate has a probability of 10 to the minus 70 to be functional, whereas we find some probabilities which are finite numbers. 30% out of all, and then we can, if we go below, so there's lower energies, it's 40%, and then we can use actually the the results on the natural data to predict if the non-natural are functional, and we even go up to 80% or so. So this was what I wanted to say. I have to say thank you to a lot of people. So the ones which are in blue are the ones which contributed directly to some of these works, also the one I did not show you, but and the others are have contributed to this kind of field because we didn't come to this in short time. Thanks.
Is there any question?
Yeah, your last slide was very intriguing indeed. So
This one?
No, the one before, of course. No, so I was wondering, all these design sequences, do you know that they actually are folding to the correct functional form? Did you? I mean, obviously they are functional, so they should
we
be,
know that they function. We don't know if they are folding. So we just say, okay, they should be folding, because if not, they would not be functional. But obviously, these are a few thousand points, and we cannot do all this number of structures. What we actually did is we took about 10 sequences, half of them natural, half of them designed, but natural from other species, and we did some detailed biochemical assays to measure rate constants for their catalytic capacity. And the ones we generated are slightly worse than naturals. So probably if you do a bit of optimization, so what people in protein do is what is called directed evolution. It was Nobel Prize in 2018 in chemistry. Yeah, exactly, Francis Arnaud. And what you do is you introduce some mutations and a strong selection, and like this typically you can refine function. Probably this would bring them very easily to natural-like function. Here they are slightly worse, but really only slightly worse.
So in these 2 days, there has been a lot of questions of coarse graining when you have, say, a protein and you write it with all its atoms. And here somehow you are working with something which is a bit of a coarse grained version of the protein, which is just a sequence. And so here you say, okay, we are doing hundreds of mutations. We couldn't do the structures of this, but does anybody have tried to use... So you start from an initial structure that you know. Mm-hmm. You do mutation at the level of the coarse grain, I mean, in the sequence of amino acid. So you could try to think that, okay, the structure should be somehow not too far from the initial one, and to try and follow your mutations amino acid after amino acid with an all-atom simulation, which does anybody try that?
This is quite complicated. So these are about 100 amino acids. So if you want to do some molecular dynamics which sees unfolding and refolding, this takes a long time. So that's not easy. What you could try to do is to predict if these still have the correct structures. The problem is that predicting structure for individual sequences is still hard. And what AlphaFold, for instance, does, it looks for natural homologs and uses an alignment and predicts a structure using the alignment. And there this coevolution information comes in. But if you have something which is recognized as a homolog of these natural sequences, because it has a similar sequence statistics, and then I give it a lot of natural sequences, AlphaFold will predict me the right structure. Even if I take 5 or 10 of my generated things and give them just to AlphaFold without allowing AlphaFold to find other sequences, it gives almost precisely exactly the same structure. But I wouldn't count too much on this. because AlphaFold is trained on existing well-formed structures. So it tries to predict a well-formed structure. And so it's not necessarily very sensitive on predicting destabilizing mutations which lead to unfolding.
Alchemically from one guy to another by transmutating one amino acid to another without having to unfold the whole thing and to fold it back again.
That's what actually we would expect that the sequence space is kind of connected because they all come from natural evolution, so from one common ancestor. So there are paths connecting them, and we are actually, together with some experimentalists, we are exploring the space between two natural proteins, but it's again, in this case, it's the 140 mutations from each other. And if you just look to the mutations which bring one to the other, it's already 2 to the 140 sequences, which is a bit. And we can test a few thousand. So we are.
That's why it's simpler in your model, because you can choose that there is only one mutation when you generate. I know maybe you cannot do that depending on what is your MCMC.
We can do one mutation. We can do. These are IID sampled, so they are sometimes up to 40 mutations away from each natural sequences we had in the data. Most are a bit closer, but also the closest sequence are closer than. Here we didn't look to making mutational paths. This is actually the part which I didn't show you about was about modeling evolution mutation by mutation.
Just a short. Did you actually present the model? You actually said that you have the energy as function of amino acids, and that was the model. But
no, I did not present here.
So what is the model that you're using?
The model is a very simple POTS model in this case. It's just that I write that P of an amino acid sequence of length L is proportional to exponential sum I j I j a I a j plus sum over I h I.
And the J are some coupling constants?
And these are couplings between.
Neighboring.
No, they are between any pairs. And they are, in principle, these are necessary to get the Fi of AI. These I needed to actually be able to fit the Fi j AI aj. And what I do is basically I try to fit these parameters such that the sum over A1 to AL P of A1 AL delta AI A delta AJ B is Fij of AB. So that the marginal distribution of my model for individual and pair of site coincide with this was the empirical one which I had from my alignment. This is a nice model for this because for this model these two are sufficient statistics, or for this statistic this is a maximum entropy model. Just that calculating this is obviously something which I cannot do analytically, but we have to do by sampling.
It's not called now.
We are running out of time, but I cannot resist. And how do you sample then once you have trained your POTS model? And in a sense, how different are the sequence you obtain? I mean, how many mutations do they have? Do you have sampling problems in getting diverse sequences after you did your model, since you also set that for yourself as an objective?
So
question on how you explore once you've learned.
The models are typically look quite ergodic. They can have relatively long time scales sometimes.
amino acid single flip, single and.
And what we do is Gibbs sampling. It's working a bit better than Metropolis in these cases, but you can do Metropolis. But it's single amino acid. Sometimes you have to wait, so you have to be sure about decorrelation. So you have to, I don't know, correlation along individual chains, compare with distinct chains and so on, to be rather sure. But we need it even for the learning. And in some cases, actually, it gets complicated. There is an issue sometimes. So what helps if you have a problem is you put a bit of regularization, because regularization makes all parameters smaller. This is like higher temperature, so you sample more easily.
Thank you.
But it's okay. It's okay.
But you don't have metastability, because that's the obvious problem. No? If you do local sampling, it's fine.
Well, you have sometimes correlations with do like this, and then so kind of relatively slow dynamics. But this is typically if you have overparameterized models. And then there are models which actually in sampling are very easy. I mentioned these autoregressive models. Their sampling is just immediate. Yeah, but so the autoregressive has lower entropy than this one. We find typically, which is maybe not astonishing because this is a maximum entropy model, but this is waving hands.
Okay. Let's fix again.
My God. It's not.
So I'd like first to thank the organizers for inviting me to give a talk here. So today I'm going to be talking, as I said, about normalizing flows for lattice QCD. But before I start, I should say that all of this is work that's done as part of a larger collaboration. There are a good number of us who work under Fiala Shanahan at MIT. We also have some collaborators at DeepMind, as well as people at Bern, Wisconsin, and NYU. So all the work that I'm going to be talking about was done by some of the, in collaboration with all of these people. So to give an outline of what I'm going to say here, first thing I'm going to do is I'm going to talk about lattice QCD. What is it? Why do we care about it? And how do we perform calculations with this? Then I'm going to talk about normalizing flows, which in this context will be a tool that we're going to use for a sampling problem that comes up in lattice QCD. Then I'm going to talk about some of the particular challenges of applying normalizing flows to lattice QCD. And then I'm going to give some overview of some results and look forward to what we're going to do in the future. So in order to tell you about lattice QCD, first I have to tell you about the QCD part. So QCD is quantum cobordynamics. This is the theory of the strong force. As I presume everyone here knows, everything that we see and interact with is made up of atoms, which in turn are made up of protons, neutrons, and electrons. But it turns out that the protons and neutrons themselves are not fundamental particles. They are made up of smaller particles called quarks that are bound together by gluons. And the theory that describes how these quarks and gluons come together to form protons and neutrons is the theory of QCD. So where is this useful? Why do we care about this? Well, one good example of where QCD is highly relevant is looking at, say, particle colliders. If you think about something like the LHC, every aspect of the LHC in a collision really is influenced by QCD. If you look at the initial states, these are protons coming in. These are bound together by QCD. QCD is an important interaction in terms of thinking about how these collisions happen. And then also the things that come out of it and the things that we measure are also often bound together by QCD. So if you want to understand what's going on at the LHC, you really need to understand QCD very well. But another example that also where QCD is relevant is in looking for things like searching for new particles, things like dark matter direct detection experiments. So these are these types of experiments where we're trying to look for some new hypothetical particle. And the way that we often do this is by taking the biggest target we can find. You can think of a big nucleus, something like xenon. And then we try to see if this particle is going to scatter off of it. But the xenon nucleus itself is bound together by QCD. So in order to understand how a hypothetical dark matter particle would scatter off of xenon, we really need to be able to understand how QCD works. And so as it turns out, we're quite lucky in that we do have some tools to be able to work with QCD. In particular, one of the tools that the tool that I'm most focused on is the tool of lattice QCD. So lattice QCD is the only systematically improvable way we have to really attack the physics of QCD when it is a strongly interacting theory. It is kind of a brute force approach. We discretize space and time, and then we end up doing a very high dimensional interval. To give you a sense of scale, in a typical state-of-the-art calculations, we'll be looking at something like a multi-billion dimensional interval. So, of course, I'm trying to evaluate this with something like Riemann sums. It would be kind of silly. So instead, we evaluate it with Monte Carlo. The integral that we're looking at is this kind of Boltzmann distributed thing here. And we can go ahead and draw samples proportional to this e to the minus s Boltzmann factor. And we're able to compute the expectation values you want. And using this, we're able to compute some physical quantities and be able to get some understanding of the physics as we want to understand it. But as with many fields of research, though, there's a lot of things we do understand. There's a lot of things we can calculate. There are also things that really prevent us from going further. There are things that we want to calculate, but we're not able to because our tools really don't help us, or our tools really don't work, or don't scale very well. So one particular example of something that really slows down state-of-the-art lattice calculations is the problem of critical slowing down. So to understand this, you have to talk about, have to understand that usually we're using Markov chain Monte Carlo methods. In particular, HMC is the usual algorithm that we're using for this. And all of these algorithms, though there are some cleverness, and I know there are many talks here that have talked about some of the cleverness you can do with this, but at the end of the day, all of these are really kind of based on local updates. We're moving some small distance through the configuration space. You can think that, in some sense, all of these are really just fancy random walks through configuration space in one way or another. And the problem with this is that that means, because these are local updates, it means that the kind of decorrelation that we're going to get, because we need to decorrelate our samples, we need to go long enough to be able to get an independent sample, these steps can only really decorrelate us on the scale of the lattice spacing, which is the spacing between adjacent lattice sites. And the reason why this is such a problem is because in lattice QCD, we really need to take the limit of a to 0. This is because when we're talking about this lattice in lattice QCD, this is not a physical lattice. We're really only putting this lattice here because we want to make the problem finite. But at the end of the day, we want to get rid of this. So we need to take this what we call the continuum limit, which takes a to 0. But as I was saying, the kind of rate of decorrelation is proportional to a. So we're taking a to 0, but this is kind of making our sample problem harder and harder. So then we keep on getting things keep on slowing down as we're taking this limit that we really need to take to be able to extract the physics we want to extract. So then and this gives you plots like the one that you can see here. So you can see this is the integrated autocorrelation time. So this is some measure of how much effort you have to put in per sample. And on the x-axis here, you can see this is the lattice spacing in femtometers. So note that this is a log scale on the y-axis here. So as you're going to the left here, the problem is getting much, much harder. And But the thing is, we really need to take this limit. This is where we want to go. We kind of want to get even off to the left of this plot, but it keeps on getting harder and harder. And this might sound bad enough looking at this, but it turns out it can be even worse and be actually exponentially bad due to a problem that we call topological freezing. So topological freezing is a consequence of the fact that the distribution of QCD, like many distributions, is multimodal. So you can think that projected along some axis, the action or energy of our distribution looks something like this. You have a whole bunch of different separate modes, and you really, if you want your sampler to work correctly, you should be sampling all of these different modes with some frequency. But in practice, because of local updates, you end up finding that you very rarely jump between these modes. And in particular, when you take the continuum limit, this actually gets worse and worse. So you tend to get really stuck, and then you end up with a situation like I've shown on the right here, where you can see that most of the samples are really all just in 1 or 2 minima, and you don't actually explore the full space, and you end up with biased results. And all of this really underscores the idea that we should really be looking into the idea of non-local updates. Updates that don't just move us some epsilon distance through the space of configurations, but instead it allows us to jump around. So we can jump around between these different modes, and we can avoid critical issues like critical slowing down. And this is where normalizing flows enter the picture. So as Mary Lou talked a little bit about earlier today, normalizing flows are a method of creating probability distributions that are both easy to sample from and have tractable densities. So you can think that we start on the left here with some easy to sample prior, some Gaussian thing over here. We then apply an invertible map, and on the other side, we end up getting some new probability distribution. If all of these things are tractable, if the prior is tractable, the map is tractable, and the Jacobian of the map is tractable, we then get a tractable density that is on the other side. So the idea from machine learning here is to make this map F some highly parameterizable thing. You put a whole bunch of neural networks in it, and you figure out some way to make this happen. And then we can perform gradient descent, and we can think of training this P tilde F, training our distribution so that it matches the target distribution we want. And remember, for QCD, we know what our target distribution is. We know exactly what the energy function is. So we really, if we are able to actually train something so that these really are approximately, so that this P tilde F really approximates our target distribution well, then we're done. We can just sample this directly, and we can sample this directly quite easily. I also should note, as an aside, it really is very important for us in Lattice QCD, the fact that you can turn this into an unbiased sampler. I'm not going to talk about this too much in detail today, though Mary Lou talked a little about it in the morning. But this is actually very important for us because we really want to make sure that we get that we can kind of get this systematically improvable idea where we're really going towards the right result. So to give you a concrete example, here's an example of a scalar field theory, a normalizing flows for a scalar field theory. So a scalar field theory is going to be something with fields that have a real valued output at every single point on a lattice. It can be any dimension lattice that you want. And you can really think of this, if it's in 2 dimensions, as a kind of image. So you can think that the configurations look something like these things over here. This can be drawn from some action that I won't specify. Though we do know the action, it's just there would be a little bit to write it all out on the slide here. And so how can we construct invertible maps for this? Well, the idea that came from the machine learning community, even before this really entered into the minds of people in the Lattice community, was the idea of this thing called what's called a real non-volume preserving flow. So we split our prior variable up into 2 different parts. And for the first part, this ZA, we just output it immediately. We take our output, it's the exact same thing as the input. We call these variables frozen because they don't change. But then for the second variable, we do this kind of point-wise rescaling and translation via these arbitrary functions S and T that only depend on the frozen variables. So it's actually quite easy to see that this is actually an invertible map. Because if you look at the frozen variables, well, you didn't do anything to them, so you can just recover them immediately. That's easy. And then for the unfrozen variables, the ones that you've transformed, all the information in the transform is in these frozen variables. So you can easily undo it. And you can see the formula right here. You just undo the translation, undo the scaling. In terms of the Jacobian of this map, it turns out that the only real thing that gives you a Jacobian here is this point-wise rescaling. And that gives you a nice, easy to compute determinative of Jacobian, which is just a product of all of these scaling factors. And so lastly, once you have this, you might worry that, well, this isn't a particularly expressive transform since we haven't transformed half our variables, but we can just go ahead and swap back and forth as to which variables are active and which variables are frozen, which ones we're changing versus not changing. And this will give us some nice expressive flows that we can go ahead and build. And so this was a nice example, and this is something that you can do. But at the end of the day, our goal is not to sample scalar field theories. Our goal is to sample QCD. So what makes QCD different? Why why can't we just directly apply the methods that I'm talking about here to QCD? And it turns out there's a number of things that make QCD difficult and really end up requiring new technology in order to be able to sample from it. The first is that QCD, the variables in QCD are not real valued variables. They're not the typical things that you usually see in machine learning. They live on compact manifolds, things like something like a circle, right? And so normal technology for normalizing flows usually doesn't work, usually is designed for real numbers, but not for circles. So that technology had to be developed. The second point is this issue of gauge symmetry, which I'll get into more detail into exactly what this is in a moment. But this is a symmetry of the theory. And in theory, you could just ignore this entirely. You could just say, I don't want to worry about this symmetry and let the flow figure it out for yourself. But it turns out that we found in practice, in order to have any chance of getting efficient flows, you really need to incorporate this symmetry exactly. And lastly, there's an issue that I won't talk too much about today, but there's also this issue of fermions, which at the end of the day, we'll get into looking at determinant estimators and trying to use machine learning to work with determinant estimators. I'd be happy to talk with anyone if you wanted to talk about this in more detail sometime later. So to talk about the first point, I first have to give a little bit of mathematical background. So one of the fundamental objects of study in lattice QCD and really in all of particle physics is the idea of a Lie group. So a Lie group is really just a fancy term for a group manifold. A group that is a manifold or a manifold is a group. Take your pick. So there are only really two Lie groups that I'm going to want to talk about today. The first one is U1, which is really just the set of complex numbers of magnitude 1, so the unit circle in the complex plane. So this is just a circle. And the second one is which is perhaps slightly less familiar, is the SUN, which is the set of all complex n by n matrices satisfying this certain condition here, that its adjoint is its inverse and its determinant is 1. One way that you can understand what SUN is and get some intuitive idea of what's going on here is to think about what happens if you replace the complex numbers here with real numbers. If you do that, you actually just get this group of all rotations. You get SON. But so this gives this interpretation that you can think of SUN kind of as like complexified rotations. They're n-dimensional rotations, but they're on complex variables in some sense. And one other kind of aside that I just want to state here to make things clear is that there's a nice distribution on all of these spaces. In fact, there's a nice distribution on just about every Lie group, which is called the Haar distribution. This is really just kind of the uniform distribution. For the case of U1, it is literally just the uniform distribution of the circle. For SUN, it gets a little bit more complicated, but it is something that we do know how to easily sample from, and we can easily evaluate its density. So this will actually end up being very useful, and that this will usually end up being our prior. So with some of the mathematical preliminaries out of the way, I can tell you a little bit more about QCD and about gauge symmetry. So the fields or the kind of variables of QCD are going to live in either U1 or SUN. And really, I should say that QCD is technically is SU3, whereas if you use a different group here, it really is just we would just generically call this a gauge theory. But I'm just going to say QCD for simplicity. So these U-mu's, they live on the links between sites. So you can think over here that you kind of have U-mu carries you from x to x plus mu hat. It lives on the link between sites. So the gauge symmetry is this kind of very peculiar and very important symmetry to understand about QCD. And for this symmetry, you can pick a G-valued thing, so a U1 or an SUN valued variable at every single site in your lattice, and then you can go ahead and transform your gauge lengths in this fashion here. So you can see that U-mu will pick up a factor that's kind of at both of the ends that it's on. So this U-mu of x picks up a factor both at x and at x plus mu hat, but it picks up a different omega on each of those sites. So what I mean by symmetry here is just that our target distribution here is invariant under the action of this group. So one way to understand why this is so paradoxical and why we really end up needing to understand gauge symmetry and really incorporate it into our models is to think about what you can do to an individual gauge length here. Note that omega of x and u in this formula are both elements of the same group, and you can choose omega arbitrarily. This means that you can really make u-mu be whatever you want with this formula. You can always apply a gauge transformation to fix u-mu to whatever you want, and so you can kind of imagine you can remove any gauge length from your action. So what this is telling us is that the kind of physics of QCD, the distribution is not in any individual gauge length. Each individual gauge length tells you nothing about what the distribution is. really you have to consider kind of the ensemble of gauge links together. And if you were to try to build a flow that really just operated on these gauge links directly, then you would find that it really can't figure out what's going on because it's transforming something that's meaningless from the perspective of this theory. So how can we incorporate this symmetry into our theory? Well, the simplest thing to think of is that since the gauge symmetry means that our distribution is invariant under this action, we require that our model distribution is also invariant under this action. And kind of the simplest way to guarantee this is to go ahead and put two conditions on our flow. The first is that we're starting from something gauge invariant. So we require that our prior is going to be gauge invariant. It turns out that this will actually be relatively easy because we can simply take every link to be the hard distribution, the one I mentioned earlier. And some nice properties of the hard distribution imply that this is immediately gauge invariant. Now, then the second point, which is the one that's going to end up being a little bit more work, is gauge equivariance. This means that you can apply a gauge transform either before or after you apply this map F. And so if you put these two things together, you'll get that your model is gauge invariant, and you'll get a picture like the one that we have here on the left. So you can imagine that this is the kind of there's kind of a flat direction here that corresponds to the fact that there's a symmetry here, this kind of continuous symmetry. Whereas if you didn't do some kind of gauge invariant thing, you get the picture more like what I'm showing on the right, where it's kind of like trying to replicate it. It still has to figure out the gauge symmetry, but the gauge symmetry is just a fact about the theory. But it's really, the model would really have to put in a lot of effort to be able to discover the symmetry, whereas on the left, we get it completely for free. We don't have to put in anything. We've all automatically put into our model. So how can we construct these gauge equivariant flows? So it turns out it does take a little bit of work, but I'll go through this in a little bit of detail. So on this diagram on the right, this kind of gives a general outline of what it is. I will go through each of these steps layer by layer. The general idea here is going to be to look at trying to transform the gauge invariant degrees of freedom, the degrees of freedom that don't change under gauge transformations. So you can think that as you go in through the layers of this transformation, the smaller and smaller boxes, you get things that transform more and more simply under gauge transformations. So in particular, I'll show you that you can go from gauge equivariance to conjugation equivariance, and then down to permutation equivariance. And this will kind of let us break down the problem until we're just operating on real numbers. And we know how to do flows on real numbers. So once we get this kind of down, then we can apply some map on the real number, on the kind of gauge invariant degrees of freedom that we've extracted, and then we can go ahead and use that to update our gauge link. Now here I'm going to, for the sake of simplicity, I'm going to talk about just updating a single gauge link U. So you can imagine like the scalar field theory I talked about before, that you usually will try to freeze some number of variables and update the other variables conditioned on them. But here I'm just going to think about the simple case where I just take one gauge link, I want to update that one gauge link, and I freeze everything else. Though in practice you would likely do something more parallel. And there's also a reference here in case anyone wants to dig in, look at this in more detail. So I'm going to start with the example of U1 because it turns out U1 is a little bit simpler than the case of SUN. So the key idea of trying to make gauge equivariant flows for U1 is to try to think of transforming this object that we call the plaquette. So you can write out this product, the plaquette, as a product of gauge links, as I've written out here. But the real way to think about the plaquette is as this picture that I've drawn in the upper right. It's this thing where the gauge links kind of go in a circle. They're gauge links that carry you around in a circle and land you back at the same point where you started. So if you go ahead and look at the gauge transformation properties of this, all of these different U mu's under a gauge transformation will pick up a bunch of omegas at a bunch of different sites. But since it's going in a loop this way, it actually turns out they all will cancel. You'll get that this plaquette is actually gauge invariant. What this means is that we can think of trying to transform the plaquette rather than trying to transform the gauge link. In particular, we can define some map from U1 to U1 that updates the plaquette. And then we can go ahead and reverse engineer how we could have changed the link to be able to then get the plaquette to be updated. And this will be automatically gauge invariant. So in particular, you can see the exact formula that we use here. You can think we start with our gauge link, we quotient out the plaquette, the old plaquette, and then we multiply by the new plaquette. This will change our plaquette to be the new value, this h of p value, and it will be a gauge equivariant transformation. So now how does this work when we go to SUN? Well, SUN is, yep.
Here, you have, so for mu, so you have one link that is indexed by mu, you have to choose a plaquette. So
yes.
How do you partition your system? Do you have a choice, or is it that?
Yeah, so you do have a choice. And in general, what we will actually do is kind of choose different directions and different directions for the plaquette to go, and do this all in kind of an iterative fashion where we make all of the different choices one after another, similar to how with the scalar field theory, we're kind of swapping things back and forth, what's active and what's frozen, so that everything's getting updated at different times. Yeah, so there is some degree of choice here. So for SUN, the idea is still pretty similar. We still want to think about transforming the plaquette, but it turns out for SUN, the plaquette is no longer gauge invariant. You still get a lot of cancellation, but at the end of the day, if you put in all the factors, you see that the plaquette will actually transform like this. It picks up, it kind of gets conjugated under the gauge temperature at a single site. Now, this might not seem like this is all that different, but this really is actually a lot nicer, because we've now gone from a property up top here that is acting on multiple sites, where we have to deal with multiple different sites, and now we can just work on one site. In particular, we can still think of transforming the plaquette as before. We're going to have some function from SUN to SUN, except now there's going to be an additional condition on this function that is going to be this conjugation equivariance, which is going to tell us that in some sense this function has to respect the action of the gauge symmetry on the plaquette. So if we can make a function that is gauge equivariant on SUN, then we can use that to construct a gauge equivariant flow for SUN. So how can we construct a function that is conjugation equivariant? So this goes under the name of spectral flows. The idea, again, is to transform the gauge invariant degrees of freedom, or in this case, the conjugation invariant degrees of freedom, which, as it turns out, are the eigenvalues of a matrix. In particular, we can take any matrix in SUN and we can diagonalize it. You get something like this. All of the eigenvalues are going to end up being pure phases because SUN is because of the condition of x dagger x as being the identity. And then we can think about trying to kind of apply a transform on these theta variables or on the eigenvalues. So in particular, we define the action of our function h by defining an action on the angle variables that exist here. Now, there are still some subtleties that you have to work out here that you have to be careful about. In particular, the first thing is that we have to be a little bit careful about the order here, because the eigenvalues of a matrix don't have any canonical order. And there isn't necessarily a canonical way to order these things that all live on the unit circle. But it turns out this is actually relatively simple to solve. All you have to do is choose a canonical order. We just come up with we basically make our own canonical order. We choose an arbitrary way. We come up with an arbitrary procedure for sorting eigenvalues effectively, and that allows us to kind of have a well-defined order for this. And that works out nicely. The last one, the other point is that these theta variables actually aren't independent, as it turns out. And this is just because the product of all the eigenvalues is the determinant of the matrix, but for SUN, the determinant is going to be 1. But this is also relatively simple to deal with. We just remove the value theta n. So to kind of give a recap of what we've done, we've gone ahead and we've done this kind of reduction of the problem to simpler and simpler terms. So in particular, we started with trying to perform gauge equivariant transformations on gauge lengths. We then looked at trying to transform the plaquette, which is a slightly simpler object to transform. This, in the case of U1, at this point we were done. We already had gauge equivariant flows. But for SUN, it turns out we have to do a little bit more work, and we have to start thinking about the transformation properties of the plaquette, in particular extracting the eigenvalues of the plaquette and performing our flow on those eigenvalues. And so, as Mary Lou was alluding to earlier, once we have this kind of flow, we can go ahead and take a whole bunch of these and stack them together and apply a bunch of transformations that will transform different gauge lengths, making different choices along the way. And we can use this to chain together to make equivariant flows that are arbitrarily expressive. So now, given that we have these equivariant flows, what can we do with them? And it turns out there are already some interesting results that we've been able to get in terms of just with these equivariant flows. So this is an example of a U1 gauge theory in 2D. So the gauge group here is U1. And here you can see on the y-axis, there is a log scale of the integrated autocorrelation time. So this is an effort per sampling kind of thing. And so you can see there's 3 lines here. The 2 on the top, the blue and gray points, those are both classical algorithms that people often use in practice to be able to sample these kinds of theories. And meanwhile, in the orange, you can see the gauge equivariant flow that we've built. And the scaling here is really much more favorable. And you can really see how, and going to the right on this axis is really the epitome of critical slowing down. So you're kind of seeing that this has really alleviated a lot of critical slowing down. And in particular, the flow really only gets a factor of a few harder, whereas, for instance, HMC is 10,000 times harder to be able to sample at these parameters. Another example that I can show here is an example of a theory with U1 and fermions. I haven't told you too much about fermions, but we have been able to integrate these kinds of things into our models. And in particular, this plot here really shows kind of the epitome of topological freezing. You can see when you're using HMC, you're living up in these kind of gray or these red points. And as you're adding more samples going along the bottom here, you can see that you really think that you found the value. You think that the actual value is up here on the top. But then all of a sudden, you get a random tunneling event. It's like one of these rare events that we've been discussing very often. And suddenly, when you get that tunneling event, you realize that you've actually been sampling from just one of the modes. And there's another mode that you've entirely missed. So you really have no idea what's going on. So then suddenly, your error bars blow up. The central value jumps a whole bunch. And in the case of the gray model, you may not even realize that this is happening. Meanwhile, the flow model, which is in blue here, doesn't suffer from any problems like this. It just slowly converges. It gets nicer. It gets kind of you get this kind of nice 1 over root n errors, and it just slowly converges and gives you a much more precise value at the end of the day. And lastly, we have just recently been able to put out the real first example of sampling QCD configurations. Now, this is still really at relatively small parameters. It's a small lattice. It's easy parameters. And so in the future, we're really looking forward to trying to scale these models up. And this is one of those things that we're going to be looking for in the future. And this is also something that we'd love to take input from anyone who has any good ideas in terms of being able to make these models more expressive and to be able to scale them up to larger lattices. So with that, that's all I have on my slides. And I would open the floor for questions.
Thanks a lot for the great talk. I think half an hour to be pedagogical on lattice QCD is quite impressive, apart from the rest of the results, which also are very impressive. So could you give us a sense, indeed, of what's the dimensionality of the models which you have been tackling so far, and maybe also how do you train? Because this is something that which data you use and so on and so forth.
Yeah, so for these models, these 2D models are all on, I think, 16 squared lattices. The QCD result is really, I think it's a 4 to the 4th model. So it's really quite small in the scale of lattices that we want to look at. So in terms of training, I believe I actually have a slide on it. We really just use the reverse KL. So we generate samples from our model and train based on that. So we use this loss function. Well, so it turns out that if you kind of look at the mode structure of QCD, so this really is an accurate picture of the mode structure. It really is just an integer valued thing. So in particular, the Haar measure, since it's this kind of uniform measure, it really captures all. It's kind of these modes are kind of like things that are kind of wrapping around. There's some kind of homotopy group going on here. Since you start with the Haar, it really starts sampling all of the modes kind of evenly. So we really haven't found too many issues with mode collapse in this case.
Right now, but I missed quite a few points, I think, along the talk. So it's related to so you pointed out that you have the question of local move don't work. So at the end, you have something which works. Is it only because of the flow as we had in a normalizing flow, or is it also related to the fact that you have these plaquettes which are somehow a bit less local than just
So it really is the fact that these are kind of non-local. These are kind of global updates. We're doing kind of We're doing kind of an independence metropolis type thing. So the updates are kind of entirely independent.
So it's related to the fact that you are using flow models and not to this the fact that you are incorporating gauge symmetries.
No, I mean, for instance, HMC is also gauge invariant in a certain sense. So this has already been integrated into those models.
I have one.
Regarding so you said with the dimensionality, you have a 4x4 lattice, something like that. So,
4 to the 4th, yeah.
So how close is that to like real lattice QCD? Like how far are we from?
So there is quite a lot of scaling that has to be done here. So like a typical scale of the lattice calculation you might see might be something like 48 cubed by 96. Okay. So there's a lot of scaling that needs to be done here.
And does the the experiments, I mean, like the theoretic, like the experimental results that you get now, like, do they make sense from a physics point of view? Like, are you recovering, even though you still are not close to the experimental setting, can you still make, I don't know, prediction out of it, or?
So you're saying in terms of like physical predictions?
Yes.
Or?
Yeah.
Yeah, so a lot of these models really are kind of like toy models. So in particular, this model that I'm showing here, this U1 plus fermions, this is called the Schwinger model, and this is commonly used as a kind of toy model for building up the QCD. This is usually the test bed that people use for their algorithms. So in particular, for instance, there is kind of a truth line here. We do know how to be able, we do know some very clever things that work to be able to give us this truth line, though those, in practice, those don't actually work for QCD itself, because the Schwinger model is a little bit nicer. Yeah. So in terms of physical results, really we need to scale up QCD to be able to do physical results.
Thank you.
Any other questions?